Before your eyes grow heavy with the quiet weight of another day, there's a question that hums beneath the stillness of sleep, a question as old as wonder itself. What is reality? Is it the solid weight beneath your feet, or the flicker behind your eyes? Is it made of matter and motion, or something far stranger? A truth that trembles in the invisible spaces. Tonight, we follow the thread not just of knowledge, but of mystery. We go where the world dissolves into probabilities, where particles choose paths only when watched, and where the tiniest moment holds an infinity of possible futures. This is not just physics. This is a journey into the very code of existence. You don't need to understand it all, you only need to listen. And let your mind open like the sky. So wherever you are, whether in bed, on a quiet walk, or gazing at a ceiling you've seen 1,000 times, let this be your companion through the dark. Let each word be a soft breath of wonder. Let each chapter be a deeper descent into the mystery that surrounds you and is you. And as you listen, ask yourself not just how the world works, but why it feels so strange to be alive inside it. Now, breathe, settle into the unknown, and come with us to the place where it all begins. The quantum realm awaits. Chapter 1. The Quantum Awakening. When physics met the impossible, there was a time when the universe made sense. The apple fell from the tree, and the moon traced its path around the earth, not because of mystery, but because of Newton equations marched across chalkboards with clean precision, and reality obeyed laws as strict and absolute as the ticking of a grandfather clock. Scientists could predict the paths of planets, the rise of tides, the fall of cannonballs with a confidence that bordered on divine certainty. It was a world of smooth trajectories, cause and effect, predictable outcomes, and one universal truth. If you knew where something was and how fast it was going, you could know where it would be forever. But then something strange happened. In the early 20th century, tiny cracks began to form in the marble of classical physics, not in the grandeur of galaxies, but in the smallest, most delicate particles of existence. Light, which once seemed so familiar, began to behave in deeply unfamiliar ways. When scientists shined beams of light through two narrow slits, they didn't get neat patterns of brightness and shadow. They got something else entirely, something that danced between order and chaos, something that whispered of an underlying reality stranger than anything imagined before. The experiment was simple, and yet it changed everything. Fire photons, particles of light, at a screen with two slits. Expect them to go through one or the other. Expect them to hit the back wall and form two piles. That would be logical. That would be Newtonian. But instead, what emerged was a pattern. An interference pattern, as if each photon had passed through both slits at the same time and interfered with itself, and worse, or better, depending on your thirst for wonder. If you tried to observe which slit the photon passed through, the pattern vanished. The moment you looked, the magic was gone. The moment you measured, the mystery dissolved into something dull and familiar. What was this? It wasn't just a failure of old equations. It was a deeper rupture, a revelation that the very act of observation changed what was real. It was as if the universe refused to reveal itself fully, unless you asked a specific question in a specific way, and even then, it only gave you part of the answer. You could know where a particle was, but not where it was going. You could know how fast it was moving, but not where it would be. Not both. Never both. That was Heisenberg's uncertainty. And it wasn't a technological flaw. It was a fundamental limit. Reality, it turned out, was not carved in stone. It was painted in probabilities. Welcome to the quantum world. This was the quantum awakening. A slow, uneasy opening of eyes to a realm where particles are not particles in the way we thought, and waves are not waves in the oceanic sense, but something more abstract, more mathematical, more ethereal. It is a place where electrons orbit not in neat circles but in cloudy maybes, where existence itself seems to flicker in and out of being, as if the universe only realizes it's real when something watches it. It began with Max Planck, who, in trying to explain why hot objects glow the way they do, discovered that energy doesn't flow smoothly, but in discrete chunks. Quanta. A radical idea, and yet one that opened a door. Then came Einstein, who proposed that light itself was made of these quanta packets of energy we now call photons. Suddenly light was not only a wave, but also a particle. And particles in turn began to exhibit wave-like behavior. Everything blurred, categories collapsed, certainties crumbled. And into this confusion stepped a new kind of physics. One not of certainty but of probability, not of absolute truth, but of statistical expectation. The equations worked more precisely than anything before, and yet no one could say what they meant. The quantum revolution did not simply offer new answers, it forced us to ask new questions. What is a particle? What is a wave? What is real? And what does it mean to observe something? To measure it? To know it? At its heart, quantum physics does not describe things so much as it describes the likelihood of things happening. A particle is not a point in space, it is a cloud of probabilities, a wave function that contains every possible location it might be. Until the moment it is measured, only then does it choose a position. And even that word choose is misleading. For no one knows what causes the wave function to collapse, it just does, or it seems to. Some say it's the measurement, others say it's consciousness. Some even say the wave function never collapses at all, that every possibility becomes real in a parallel universe we'll never touch. But at this dawn of quantum thought, none of that was clear. Only the disquieting truth was, the classical picture of the universe had been replaced, not by a new picture, but by a new kind of shadow. Werner Heisenberg, Niels Bohr, Erwin Schrödinger, names now carved into the marble of scientific history, were not just physicists. They were pioneers of a strange new language. They argued not about experiments, but about what reality meant. They debated whether electrons existed as real things before we looked at them, or only as mathematical descriptions, abstracted from the realm of the actual. They tried to make sense of a universe that no longer played by human rules, and perhaps no figure captured this new realm better than Schrödinger, whose famous cat, both alive and dead until observed, became the symbol of quantum absurdity. His point was not to confuse, but to illustrate the confusion already at the heart of this new science. If an atom could be in a superposition, a blend of different states until observed, what happened when that atom's fate was tied to a cat's life? Was the cat in limbo until someone opened the box? Was reality itself incomplete until it was witnessed? These questions were not academic. They were foundational. They asked whether the universe is fundamentally deterministic as Newton believed, or indeterministic, probabilistic, flickering. They questioned whether there is a world out there, independent of our observation, or whether our very act of looking is what brings that world into being. And still deeper mysteries stirred. Beneath the veil of particles and forces, something even stranger loomed. The quantum field. Every particle, from the electron to the quark, is not an isolated object, but an excitation, a ripple in a deeper field that stretches through all of space and time. These fields are not visible, not touchable, and yet they are the foundation of everything. What we call particles are just tiny waves on the ocean of reality, and in the quantum sea, even empty space is not truly empty. It roils with virtual particles, momentary fluctuations that appear and vanish in a breath of time, borrowing energy from nowhere, paying it back just as quickly. This isn't science fiction, this is the best description we have, and still we are left with awe. Quantum mechanics is the most successful theory in the history of physics. Its predictions have been tested, and tested again, and never once has it failed. It underpins the technologies that power our computers, our smartphones, our MRI machines, our lasers, and our understanding of the stars. It is woven into the fabric of our civilization, and yet no one can fully explain what it says about the nature of reality. No one can point and say, this is what a wave function is. No one can answer with certainty whether particles are truly real or whether reality itself is a kind of dream we're all sharing through observation. But this is not a weakness. It is an invitation to wonder, to question, to walk to the edge of what we know and peer into the abyss, not in fear but in curiosity. Because what quantum physics tells us, above all else, is that the universe is not a machine, it is not a clock, it is not something simple enough to be fully grasped by common sense or classical thinking. It is deeper, it is stranger, it is more beautiful than we dared imagine, and it is just beginning to whisper its secrets to those who listen carefully, not just with instruments and equations, but with a kind of reverent humility, the willingness to admit we do not know everything, but we are here to find out. Even if reality resists definition, it offers clues, and the next clue lies not in light, not in energy, not in space or time, but in the paradox that lies just around the corner. Chapter 2: Wave or Particle. The double-slit mystery. If you ever needed proof that the universe doesn't follow the rules we expect, all you would need to do is set up a simple experiment: 2 slits, a beam of light, and a screen to catch what comes through. That's all. No vast particle accelerators, no billion-dollar labs, just light, space, and the tiniest opening. Yet within that humble setup lies one of the greatest riddles of existence, one that still confounds scientists, philosophers, and dreamers alike. It is the double-slit experiment, and it has changed the way we see everything. To begin, imagine light as a wave, like ripples spreading across the surface of a pond. When those waves encounter a barrier with 2 small openings, they don't simply pass through like bullets through windows. No, they diffract, they bend, spread out, interfere. The waves from one slit meet the waves from the other, and where their peaks align, they amplify. Where a peak meets a valley, they cancel. This creates an interference pattern, bright and dark bands, that show how the waves are overlapping, colliding, dancing. This is what we expect from waves. And for a long time, we believed light was a wave. After all, it showed every hallmark: interference, diffraction, bending around corners. The double-slit experiment confirmed that when a light source was directed at the slits, the resulting pattern was unmistakably wave-like. But then the twist came, quiet and shattering. What if, instead of a continuous beam of light, we fired photons one at a time? Individual particles of light, spaced out so that they couldn't possibly be interfering with each other. We expected 2 neat piles behind the slits, like grains of sand tossed through narrow holes. But what appeared, slowly and unmistakably, was the same interference pattern, the same delicate dance of brightness and shadow, as if each photon was interfering not with another, but with itself, as if it had somehow passed through both slits at once, traveled 2 paths simultaneously, and arrived at the screen as a probability wave, not a particle. This wasn't metaphor, this was measured. Again and again, each photon, when unobserved, behaved like a wave, smearing itself across multiple possibilities, existing in all potential paths. But when we set up a detector, some way to check which slit it actually passed through, the pattern collapsed. The interference vanished. The photon chose a path, became a particle, left behind 2 simple bands, like we originally expected. The act of measurement had changed the result. This is the mystery at the heart of the quantum world. Observation alters out. The photon behaves differently depending on whether we are watching. It is as if reality waits, undefined, until we choose to look, and in that moment, it makes up its mind. But what does that even mean? Is the photon making a decision? Is our consciousness creating the result? Is the world split into parallel outcomes that we only collapse into one through awareness? The answers, if there are answers, lie not in what we observe, but in the meaning behind the observation. This is where physics becomes something more, a mirror reflecting the limits of our understanding, the edge of our language, the threshold between what can be tested and what must be interpreted. Some physicists say the photon isn't a wave or a particle, but a quantum object that behaves like both depending on the situation. This is called complementarity, an idea central to Niels Bohr's interpretation of quantum mechanics. The system does not have definite properties until it is measured. It exists in a superposition, a state that is both one thing and another, neither fixed nor fully known, hovering in possibility. And yet, the wave is not imaginary. It is not an illusion. It is real in the way mathematics is real, precise, consistent, predictive. The interference pattern doesn't emerge from guesswork. It emerges from the fundamental structure of quantum probability. The photon does not split in half. It doesn't travel as a mist or a ghost. It travels as a probability amplitude, a wave function that describes all possible paths and all possible outcomes until something collapses it into just one. The question is, what does the collapsing? Is it the detector, the environment, the human mind? Each theory offers something different. The Copenhagen interpretation, still one of the most widely taught, suggests that the act of measurement collapses the wave function, turning possibility into reality. But it does not explain why. It simply accepts the rule. Don't ask what the particle was doing before you measured it, because the question has no answer. The wave function is not a description of what is, it is a description of what can be known. Other interpretations, like the many worlds theory, argue that the wave function never collapses at all. Instead, every possible outcome happens, but in separate branches of the universe. The photon goes through both slits, but in different realities. When we observe, we find ourselves in one version, but the others continue, each as real as this one, branching endlessly with each quantum event. It is a breathtaking idea that our universe is not unique, not singular, but just one thread in a vast tapestry of timeline. Every choice, every measurement, every quantum possibility splits the cosmos into new paths, and all of them are happening. But whether the wave function collapses or not, whether we live in one universe or infinite ones, the mystery remains the same. Why does observation seem to matter? This is not an idle question. It strikes at the foundation of everything we know. In the classical world, reality is objective. It exists whether or not we look. The apple falls whether we measure its speed. The planets orbit whether we track them or not. But in the quantum world, the very idea of objective reality begins to dissolve. Properties are not fixed until they are measured. States are not definite until they are observed. And even then, the result is not always predictable, only probable. The photon doesn't go through one slit or the other. It goes through both, or neither, or something in between. It is not a question of hidden variables or secret knowledge. It is a question of what is real, and what it means for something to be. And it's not just like electrons, those tiny particles that orbit atoms, build matter, carry electricity, behave the same way. Fire electrons through a double slit, one at a time, and you get the same interference pattern. Matter acts like a wave. The world we see as solid is at its core smeared with probability. Even large molecules made of dozens of atoms show this behavior under the right condition. The boundary between the quantum and the classical is not a sharp line, but a gradient, a slope, where mystery fades into predictability, not because the rules change, but because probabilities wash out into averages. Still, the question burns. What makes a particle decide? What causes the pattern to shift from wave to dot? What turns potential into reality? Some theories suggest that it's the environment, a process called decoherence. When a quantum object interacts with the world around it, its delicate wave function becomes entangled with countless other factors: air molecules, heat, light. This tangle robs it of its purity. It no longer exists in a superposition. It becomes one thing, a particle, a choice, an outcome. But even this doesn't fully answer the puzzle. Decoherence explains why quantum effects are hard to see in the macroscopic world. It doesn't explain the origin of the collapse. It doesn't explain why the act of measuring reveals a single result, not many. It doesn't explain why the universe acts as if it knows when we are watching. And so the double-slit experiment remains, not just in textbooks, but in the hearts of all who seek to understand the strange, shimmering reality beneath appearances. It is the experiment that taught us to question not just the what, but the how. Not just the object, but the observer. It shattered the illusion of separation between mind and matter, between question and answer, between being and knowing. Each photon that flies through those slits is a messenger, not from another world but from the foundation of this one. It whispers something that cannot be spoken in ordinary terms. It asks us to rethink our assumptions, to leave behind our craving for certainty, to sit in the presence of paradox and not flinch, because reality at its core may not be made of things, but of relationships, not of objects, but of interactions, not of particles, but of potential. And the next question leads deeper still into the very heart of this mystery, where a single idea shakes the pillars of what we call Chapter 3, Superposition. The state of everything and nothing. There is a word whispered often in the halls of quantum physics, a word that feels more like a spell than a scientific term, a word that unlocks doors not just into new equations, but into a radically different way of imagining the world: superposition. At first glance, it seems like a simple enough idea, the notion that a quantum system can exist in multiple states at once. But to say it that way is to drain it of its strangeness, to reduce its dizzying implications into something tame. Because superposition is not a metaphor. It is not a theoretical exercise. It is real. And what it suggests is that, at the most fundamental level, reality is not a fixed state, but a fluid combination of all possible states. A shimmering cloud of being and not being. Yes and no, presence and absence, all layered over one another like a chord of existence waiting to be played. To understand this, imagine a coin spinning in midair. While it spins, it is not truly heads or tails, it is both. It contains the possibility of both outcomes, suspended, unresolved. But the quantum world is not like a spinning coin, because when you catch a coin and see the result, you can reasonably say it was one or the other all along. We just didn't know it until we looked. In quantum mechanics, the situation is different. The system does not secretly contain a hidden outcome. It truly exists in both states, until the moment of observation. And then, only then, does it snap into one reality. This is not philosophical hand-waving. It is mathematically precise, experimentally verified and profoundly unsettling. An electron, for example, can be in a state where it is spinning clockwise and counterclockwise at the same time. A photon can be both vertically and horizontally polarized. A particle can be in two locations at once, or even in a blend of energy levels. And all of this is not because we lack information. It is because this is the nature of the system itself. Superposition is not ignorance. It is the deepest form of. In the language of mathematics, superposition is described by a wavefunction, a complex function that holds the probabilities of every possible outcome. It is not a blur of indecision. It is a structure, a symmetry, a coherence. The wavefunction evolves over time according to the Schrödinger equation, a masterpiece of predictive power. But that equation doesn't tell us what will happen. It tells us what might happen, and with what likelihood, until a measurement is made, And then, just like that, the cloud collapses, the wave function reduces, the superposition ends. One result is selected. The rest vanish as if they never were. This moment, the collapse of the wave function, is where mystery enters in full force. What determines the outcome? Why does one possibility become real while the others disappear? Is it truly random? Is it influenced by something outside the system? Is there, as Einstein hoped, some hidden variable we've yet to discover, some buried piece of information that could restore determinism to this strange domain? No one knows, but experiments have ruled out many forms of hidden variables. The violations of Bell's inequalities suggest that local realism, the idea that particles have definite properties independent of measurement, and that nothing can influence something else faster than light, cannot explain quantum behavior. In other words, if superposition is an illusion, it is a remarkably convincing one, sustained by a conspiracy of nature so precise that it obeys quantum predictions perfectly in every test ever conducted. And so we are left with superposition, not as a trick or a misunderstanding, but as a fundamental feature of the world. It is a feature we are still learning how to use. In the emerging field of quantum computing, superposition is not a bug. It is the central power source. A classical bit can be either 0 or 1. A quantum bit or qubit can be in a superposition of 0 and 1 at the same time. This means that in theory, a quantum computer with enough qubits can perform many calculations in parallel, solving problems that would take classical computers longer than the lifetime of the universe. But maintaining superposition is not easy. Quantum systems are fragile. The slightest interaction with the environment, a stray photon, a jolt of heat, even the breath of nearby matter, can cause decoherence, collapsing the superposition prematurely. Protecting qubits requires isolation, entanglement, error correction, and the engineering of some of the coldest, most controlled environments ever created. And yet, even with all this technological challenge, the fact remains, we can harness superposition. We can use it. We can build with it. And this tells us something astonishing, that superposition is not just a quirk of thought experiments, but a tangible force in the construction of reality. It also tells us that the world we see is only one sliver of what could be, because superposition means that the present moment, this moment, right now, is a convergence of many possibilities, all resolved into one reality. But behind this outcome lie the paths not taken, the states not realized, the possibilities that still flicker just beyond the edge of perception. We walk through a universe that was once a haze of quantum potential, made solid by interactions, measurements, and the silent arithmetic of probability. Even consciousness, that strange flicker of self-awareness, has been drawn into the discussion. Some interpretations of quantum mechanics, controversial though they may be, suggest that consciousness itself may play a role in collapsing the wave function, that without observation, the world remains suspended in a superposition, and it is the mind that resolves it into something definite. This is the idea behind the consciousness causes collapse interpretation, a view that remains on the fringes of physics, but not entirely dismissed. Its appeal lies not in proof, but in the philosophical itch it scratches, the desire to connect the observer and the observed in a deeper, more intimate way. But even without invoking the mind, superposition remains a gateway to rethinking everything. In a classical world, existence is a binary, this or that, here or there, true or false. But the quantum world teaches us that the deepest truths are gradients, overlaps, ambiguities. The universe does not make hard choices until it must. It hesitates. It holds its breath. It balances between all that can be, until something, a touch, a glance, a collision, causes it to decide. And even then, the other possibilities are not erased. They remain echoing in the mathematics, living in alternate branches if many worlds is correct, or simply waiting to be explored again in another moment, another experiment, another question. To accept superposition is to accept that reality is not a fixed landscape, but a shimmering field of potentials. It is to let go of certainty and embrace probability. It is to admit that, at the heart of things, the universe is not deterministic clockwork, but creative suggestion. And so we live in a world made not of things, but of maybes, not of absolutes, but of amplitudes, not of hard edges, but of soft curves, drawn by possibility and resolved by interaction. And as we press deeper into the nature of this strange layering of states, we find something even more unnerving, that the very fabric of space and time itself may not be immune to this dance, that the boundaries we once thought were absolute, position, momentum, direction, identity, are themselves defined only in relation to other things, and only when observed. Chapter 4. Entanglement. The invisible thread between worlds. If superposition is the first whisper of the quantum world's strangeness, then entanglement is its thunder. It is the feature of reality that Albert Einstein famously called spooky action at a distance, a phrase born not of wonder, but of unease. For entanglement suggests something that shatters the walls we once believed protected our understanding of space, time, and separation. It suggests that two particles once linked can remain connected in such a profound way that the state of one seems to instantaneously affect the other, no matter how far apart they are flung across the cosmos. This is not science fiction, it is experiment, it is measurement, it is real. Begin with two particles, let's say electrons, born from a common event. Perhaps they are created in a single reaction, their spins opposite to conserve angular momentum. They part ways, traveling in opposite directions. You capture one, someone else captures the other, and now you perform a measurement on your electron. You ask, is it spinning up or spinning down? You observe, and suddenly that moment of observation doesn't just resolve your particle, it also determines the state of the distant one, immediately. Without delay, without regard for the distance between them. This is entanglement. It is not a signal. It is not a transfer of information in the classical sense. No message passes between the particles, no force reaches across the void, and yet the outcome is correlated, perfectly. Uncannily, the results are not random, they are bound, like twin dancers performing the same steps on opposite ends of the stage, never looking, never signaling, but always in rhythm. At first, it seemed impossible. Einstein, Podolsky and Rosen, in their now famous EPR paper, argued that this implied an incompleteness in quantum mechanics. They believed the particles must have carried hidden variables, predetermined states that would resolve upon measurement. The universe, they insisted, must be local and realistic. That is, things can only be influenced by their immediate surroundings, and they possess definite properties, whether or not we observe them. But then came John Bell. In the 1960s, Bell proposed a mathematical inequality, a test that could distinguish between the predictions of quantum mechanics and those of any local hidden variable theory. If experiments violated Bell's inequality, it would mean that no local realistic theory could explain what was happening. And time and again, in labs across the world, the inequality was violated. Quantum mechanics was right. The world is not local in the way Einstein had hoped. The implications are staggering. Entanglement is not a trick, it is a fundamental feature of the quantum realm, and more than that, it is not limited to tiny particles, it is not confined to laboratory conditions. Entanglement is a principle that pervades reality. It can involve photons, electrons, atoms, molecules, even small mechanical systems, and in theory there is no limit. Any two systems that interact can, under the right conditions, become entangled. Their properties become interdependent, no longer describable in isolation. They become part of a whole. What does this mean for our picture of reality? It means the world is not built from independent objects, but from relationship. It means that the fabric of the universe is not stitched together by space and time alone, but by correlation, by connection, by threads of entanglement that bind one part of the cosmos to another. These threads do not stretch across space like cables. They exist outside the framework of classical geometry. They are connections in a higher dimensional sense, invisible, instantaneous, foundational, and still, they are fragile. Entanglement is delicate. Like superposition, it is disrupted by interaction with the environment. This is why we do not see entanglement in our everyday experience. The macroscopic world is a theater of decoherence, where the entangled, the coherent, the probabilistic, gives way to the apparent solidity of classical objects. But peel back that mask, go small enough, isolate carefully enough, and the truth re-emerges. The world is not separate, it is linked, invisibly, deeply. This has consequences not only for our understanding, but for our technology. Quantum entanglement is the backbone of emerging fields, such as quantum cryptography and quantum teleportation. In quantum cryptography, entangled particles can be used to detect eavesdropping. Any attempt to measure or copy the system collapses the entanglement and alerts the user. In quantum teleportation, not the science fiction kind, but the scientific one, information about a quantum state is transmitted from one place to another using an entangled pair and a classical channel, allowing for the reconstruction of a state without physically moving the particle itself. None of this violates the speed of light. No usable information travels faster than light. But still, the correlations are immediate, unexplainable by classical causality, and utterly consistent with quantum theory. But even these applications are only the beginning. Some theorists believe entanglement may lie at the heart of space-time itself, that the smooth geometry of the universe, the curvature of gravity, the structure of space, emerges from the entanglement of underlying quantum fields. This is the idea behind the EREPR conjecture, which proposes that entangled particles are connected by microscopic wormholes, Einstein-Rosen bridges. If true, it means that geometry and gravity are not fundamental, but emergent. That space itself arises from the patterns of entanglement between quantum bits of information. It is a radical thought that what we call here and there is a byproduct of quantum connectivity. That distance is an illusion constructed from correlation. That the universe is not a stage upon which events unfold, but a web woven by entanglement, with particles, planets, and people suspended like dewdrops on its silken threads. And if entanglement can stretch across galaxies, what else might it bind? Could consciousness itself be entangled? Could the sense of self, of presence, of being in the world, be shaped by invisible connections, not just with our environment, but with others? The idea is speculative. No experiment has confirmed it, but it arises naturally from the realization that quantum systems do not respect the boundaries we impose, not boundaries of space, not boundaries of time, not boundaries of identity. Entanglement forces us to reconsider what it means to be separate. It dissolves the borders between object and observer, between here and there, between cause and effect. It invites us to imagine the universe not as a collection of isolated things, but as a single entity, rippling with internal coherence, humming with unity beneath the chaos of appearances. It is not an easy idea to hold. It resists our intuition, violates our common sense, eludes our language, but it is there, beneath the measurements, behind the equations, encoded into the statistics of every experiment ever run. And what it says is this: the universe is not made of things, it is made of connections. And in the next revelation, we confront the deepest consequence of all, the collapse of the wave function, the moment when possibility becomes presence, when the universe seems to pick a path not through reason, but through interaction, not through logic, but through the strange unfolding of quantum destiny. Chapter 5: Collapse of the wave function. Who or what decides reality? There is a silence in the quantum world, a silence before the moment of decision, before the universe reveals what it has always known, but never yet shown. It is the pause between potential and presence, between the blurred fog of possibility and the hard edge of what simply is. That moment is called the collapse of the wave function, and it is as mysterious as it is essential. Without it, there would be no outcomes, no facts, no world as we know it. There would only be maybes. Endless, echoing maybes. But what causes the collapse? What force takes a wave of infinite possibilities and reduces it to a single measurable result? What, if anything, decides which version of reality emerges and which fade like ghost branches of a tree that could have grown but didn't? To ask this is to touch the raw nerve of quantum mechanics, because the equations of quantum theory, elegant as they are, do not predict a specific result. They only describe the evolution of the wave function, the mathematical object that encodes every possible state a system might assume. The wave function spreads out, changes, oscillates in time, governed by Schrödinger's equation. But the moment we measure, the moment we look, the wave function collapses. One result emerges, the others vanish. And this transition is not described by the same equation. It is a rupture, a shift, a mystery. This gap is where interpretation rushes in. In the Copenhagen interpretation, still the dominant view taught to physics students, the wave function represents our knowledge of a system, not the system itself. It evolves smoothly until we observe, and then the act of measurement collapses it. The observer doesn't simply watch reality unfold, they participate in creating it. Reality is not what it is until it is observed. But this leads to uncomfortable questions. What counts as an observation? Does it require consciousness? Can a measuring device collapse the wave function? Or does a conscious mind have to be aware of the result? Where exactly is the boundary between the quantum and the classical, between the uncertain and the definite, between the possible and the actual? No one knows for certain. Some interpretations avoid collapse altogether. The many worlds interpretation, for example, suggests that the wave function never collapses. Not really. Instead, every possible outcome of a quantum event happens, but in separate, non-interacting branches of the universe. When you measure a particle, and it chooses a position, the other possibilities don't vanish. They unfold in other universes, each as real as this one. We just find ourselves in the branch where a particular outcome occurred. In this view, there is no collapse, only branching. Reality does not make a choice. It makes all choices, and we are simply passengers on one path of a cosmic explosion of possibilities. But even this idea, as grand as it is, does not explain what it feels like to live in a world where only one version appears to us. It offers a framework, a map of branching timelines, but it does not answer why we experience a singular reality. It does not tell us why measurement seems to resolve uncertainty into certainty, why the haze of quantum maybes solidifies when touched. Other interpretations try different routes. The objective collapse theories propose that collapse is a real physical process, not tied to observation, but to mass complexity or some unknown threshold. When a quantum system becomes large enough, its wave function collapses on its own. Reality decides for itself, not because we ask, but because it cannot remain suspended forever. One such theory, the GRW, Girardi-Rimini-Weber model, adds spontaneous collapse events into the math, tiny random nudges that force wave functions to resolve, gradually turning the quantum world classical. Still others invoke information itself. In the relational interpretation, reality is not absolute. There is no universal wave function collapse. Instead, different observers have different information, and each collapse is relative to that perspective. What is real depends on who is measuring and what they know. Then there are those who look inward, to the observer's mind. The consciousness causes collapse. Interpretation suggests that the wave function remains uncollapsed until it is experienced, until the result enters awareness. It is not the measuring device but the mind behind it that brings the outcome into being. This idea touches something ancient, something mystical, the sense that awareness is not just a feature of the universe, but its source. That consciousness is not emergent from matter, but matter is made real through consciousness. And though this view is often set aside by mainstream physics, it refuses to fade, because at its heart lies the question we cannot escape. What is the role of the observer? What is the boundary between what is and what is known? And perhaps the collapse is not a thing at all. Perhaps it is a change in perspective, a shift from a question about possibility to a record of actuality. The wave function, in this light, is not a description of a real physical object, but a tool, a map of probabilities. When we measure, we are not causing anything to happen. We are learning something that has happened. The collapse, then, is not a physical event, but an update of information. It feels dramatic, but it is no more mysterious than turning over a playing card. Yet the experiments say otherwise. Time after time, quantum systems display behaviors that resist classical explanation. Delayed choice experiments, where the decision to measure a particle's path is made after it has entered the apparatus, suggest that the past is not fixed until the present resolves it. Weak measurements, which attempt to extract information without collapsing the system, show that reality yields only shadows, not full truth. Quantum erasers erase which path information after the event, and the pattern changes retroactive. In these experiments, collapse is not just an update. It is a transformation, a redefinition, a shift in what reality is allowed to be. And so we are left suspended, like the wave function itself, not knowing for certain what causes collapse, or whether collapse even happens in the way we once thought. What we do know is this: something changes when a system is measured. Something resolves when possibility becomes result. Whether it is the detector, the environment, the mind, or the universe itself that makes the decision, the effect is undeniable. We begin with a superposition, a cloud of maybes, and then without fanfare, one answer emerges, one particle lands, one path is taken, the others disappear. And in this moment, this instantaneous transition, lies the deepest question of all. Is the universe choosing, or is it revealing? Is the collapse an act of creation, or of disclosure? And as we walk deeper into this labyrinth, we find a strange cat waiting in the shadows, neither alive nor dead, neither real nor unreal, suspended in the purest form of quantum uncertainty, daring us to open the box and accept whatever truth or contradiction we find inside. Chapter 6: Schrödinger's Cat, Thought Experiment or Hidden Truth. There is a box, sealed, silent, opaque, and inside that box, so the story goes, there is a cat. This cat is not just any cat. It does not sit, sleep, or scratch. It exists at the crossroads of thought and paradox, perched upon the razor's edge of logic and impossibility. Schrödinger's cat, arguably the most famous feline in the history of science, was never meant to be taken literally. It was not born from an experiment, but from frustration, a protest, a challenge against the weirdness that quantum mechanics dared to suggest. Yet it remains, decades later, as the symbol of the unresolved strangeness that still haunts our understanding of the quantum world. In 1935, the Austrian physicist Erwin Schrödinger, deeply troubled by the implications of the Copenhagen interpretation, posed a simple, brutal question. If the quantum world truly exists in a superposition, if particles can be both here and there, up and down until observed. Then what happens when we scale that logic upward? What happens when we entangle the fate of a visible, tangible, undeniably real object to a quantum event? So he built a thought experiment. A sealed box. Inside it, a radioactive atom, unstable, unpredictable, governed by the rules of quantum decay. Next to it, a Geiger counter. If the atom decays, the counter clicks. That click triggers a mechanism. It shatters a vial of poison. If the poison is released, the cat dies. If the atom does not decay, nothing happens. The cat lives. But here's the catch. Quantum mechanics says the atom is in a superposition, decayed and not decayed, until measured. If the atom's fate is undecided, and the mechanism depends on the atom, then the poison's release is also undecided. And if the poison's release is undecided, then the cat's life is undecided, until the box is opened. Thus, the cat is both dead and alive, not figuratively, not metaphorically, but literally, in a superposition of life and death, suspended in quantum uncertainty, not one or the other, both, until observed. Schrödinger did not propose this to embrace the absurdity. He proposed it to highlight it, to reveal the deeply unsettling implication that quantum mechanics, when taken seriously, does not merely apply to electrons and photons, but to everything, including large, warm, living things, including cats, including, perhaps, us. The paradox struck a nerve. On one side were those who said, the quantum world is fundamentally different from the classical world. Superpositions happen in the microscale, but the macroscopic realm, the world of people, cats, clocks, and chairs, is immune. Somewhere, they claimed, a boundary is crossed. Decoherence kicks in. The wave function collapses. The superposition ends before it reaches the cat. But where is that line? What determines it? How big must a system be before it becomes classical? How many atoms? How much matter? The universe does not seem to offer a crisp border between quantum and classical. There is only a gradient, and in that fog, the cat remains, silent and uncertain. Others took a bolder stance. If the wave function applies universally, they said, then the cat truly is in a superposition, dead and alive, until a conscious observer opens the box. The act of measurement collapses the state. Observation doesn't just reveal the truth, it creates it. And still others reject collapse entirely. In the many worlds interpretation, when the atom decays or doesn't decay, the universe splits. In one branch, the cat dies. In the other, it lives. Both outcomes occur, but in separate, non-communicating timelines. When we open the box, we find ourselves in one branch, unaware of the other. The cat is not in a superposition, the universe is. It is a clean solution, but it raises its own questions. If every quantum event causes the universe to split, then there are countless versions of every possible world. Infinite cats, infinite yous, infinite branching trees of fate, sprawling through the multiverse. And if every possibility happens, what does choice even mean? Others propose still stranger answers. Some suggest that quantum states do not collapse at all, but instead interact with parallel minds or hidden dimensions. Others argue that collapse is real, but rare, triggered only under certain physical conditions. Some interpretations, like relational quantum mechanics, argue that superposition and collapse are relative. What is real for one observer may not be real for another. But for the cat in the box, the arguments mean little. It waits, in silence, neither purring nor still, neither stretching nor stiff. And here lies the deeper power of Schrödinger's cat, not in what it says about quantum mechanics, but in what it asks of us. Because in that box, we find more than a cat. We find our own expectations, our assumptions, our need for clarity. We find our discomfort with ambiguity, our fear of contradictions, our craving for either-or answers in a world that increasingly seems to whisper both and. The cat is not a riddle to be solved, but a mirror. It reflects the boundary between what we understand and what we don't. It sits, alive, dead, Neither, both. Not because physics is broken, but because our view of reality may be incomplete. And perhaps that's the point, because the cat forces us to ask, what is real before we look? Is the world a definite thing, simply hidden from view, or is it undefined until we engage with it? Is truth out there waiting to be discovered, or is it born in the very act of seeking? Every time we open the box, metaphorically or otherwise, we collapse the infinite into the finite. We reduce the wave of possibilities into a single line, but we cannot forget what came before, the haze, the maybe, the overlapping symphony of unrealized futures. And we must ask ourselves, how often do we walk through our own lives assuming certainty, while the world beneath our feet quivers with ambiguity? How many boxes do we carry without opening? How many decisions wait in superposition, unresolved until we finally choose to see? Schrödinger's cat is not just a cat, it is the invitation to sit inside uncertainty and listen, to breathe in the paradox and not turn away, to hold in our minds the idea that two opposite truths might coexist, and that what we call reality might be far more fluid, far more layered, far more incomplete than we have ever dared to imagine. And just beyond this strange feline metaphor, the next revelation begins to stir, a principle not about where things are, but what we can know about them, a rule that says the universe does not give up its secrets lightly, that knowing one thing means not knowing another, that uncertainty is not a lack of knowledge, but a law built into the fabric of what is. Chapter 7. Heisenberg's Uncertainty, Why We Can Never Fully Know. There is a limit, not of measurement, but of meaning. A boundary not imposed by technology but by nature itself. It is not a wall we cannot climb, but a veil that refuses to lift. Not because we lack the tools, but because the truth is not all there to be known. This is the essence of Heisenberg's uncertainty principle, the quiet, unrelenting truth that in the quantum world, knowledge is not infinite. It is constrained, entangled with the very fabric of the thing being known. It is not about carelessness. It is not about noise or error or imprecision. It is about the fundamental way the world is built, a rule inscribed in the bones of reality, one that tells us that some things, no matter how hard we try, cannot be known simultaneously. To measure one is to blur the other. To sharpen one is to smear the rest. It is not a bug, it is the blueprint. Formally, the uncertainty principle says this: the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. The tighter we try to pin down where something is, the more uncertain we become about how fast it's moving and in what direction. It is not a limitation of tools, it is a limitation of existence. But to say it that way is to barely touch its depth, because this principle does more than set a boundary between variables. It sets a boundary between questions and answers. It tells us that even the very act of questioning changes the system. That what we choose to observe determines what can be known and what must remain in shadow. Imagine holding a marble in your hand. You can weigh it, feel its texture, watch it roll. In the classical world, there is no mystery. Every property is definite, measurable, knowable. But in the quantum realm, that marble is no longer a tidy object. It is a cloud, a wave function, a spread of probabilities. To ask where is it is to force the cloud to collapse into one spot. But in doing so, you disturb its momentum. The more certain you are of one property, the less certain you become of the other. And this is not limited to position and momentum. It applies to many pairs of so-called complementary variables, energy and time, angular momentum and orientation, even the spin directions of entangled particles. In every case, nature offers a trade. Knowledge comes at a price. To see one side clearly is to turn the other into mist. This concept was proposed by Werner Heisenberg in 1927, a time when quantum mechanics was still young, still wild, still refusing to be tamed. His insight was not a rejection of measurement, but a revelation about its nature. It wasn't just that observing changes the system, though that is true. It was that some aspects of the system do not even exist with definite values until they are measured, and that measuring one excludes the other from definition. And so uncertainty is not a flaw. It is a feature, a rule of reality that says you may look here or there, but not both. You may hold one truth in your hand, but only by letting go of another. This reshaped the entire foundation of physics. Before uncertainty, science moved with the confidence of determinism. Newton's equations could predict the future of any object, provided we knew its present conditions, position, velocity, forces. The idea was intoxicating, that if we knew everything now, we could know everything later. The universe was a clock. Its future was written. But Heisenberg shattered that dream. Because in the quantum world, the now is blurry. The present is not perfectly knowable. The inputs to prediction are incomplete by design. And so the future too is written only in probability. Even if we knew all the laws, we could not know what would happen next, with certainty. Not because we're missing pieces, but because certainty itself does not exist at that scale. And yet, paradoxically, this uncertainty gives rise to some of the most stable patterns in the cosmos. Electrons do not spiral into atomic nuclei. Why? Because the uncertainty principle prevents them from sitting still. To be tightly bound would require knowing position and momentum with impossible precision. So they hover in orbitals, diffuse clouds, never collapsing, defined not by fixed paths, but by patterns of probability. Without uncertainty, atoms would be unstable. Without atoms, matter would not exist. Even the stars themselves owe their light to uncertainty. Quantum tunneling, a phenomenon made possible by the blurriness of energy and position, allows nuclear fusion to occur in the hearts of suns. Without that tiny wiggle room, those chance slips through barriers, stars could not ignite. The heavens would be dark, and so we begin to see uncertainty not as a gap in our knowledge, but as the engine of the world. It is the space that allows change, the breath that permits transformation. It is what prevents the universe from freezing into stasis. What gives birth to motion, energy, unpredictability, light. And still, the principle haunts us. Because it does not merely apply to particles, it touches our understanding of time, of causality, of the difference between knowing and being. It tells us that observation is not passive, that knowledge is participatory, that the world does not unfold in front of us, but with us, as part of us. We are not watching the film of reality, we are inside the projector. And when we try to step back, to see both the frame and the real, to grasp the position and the momentum of the world, the focus slips, the picture dissolves. Because we cannot separate ourselves from the system, we are entangled with it, defined by it, constrained by the same uncertainties that govern all things. And so we live in a universe of soft edges, of shifting certainties, of truths that flicker between being and not being. A universe that resists complete description, not because it hides, but because it refuses to be nailed down. It dances, it breathes, it waves. And as we look deeper into the quantum realm, the implications of uncertainty stretch beyond measurement. They reach into the fields beneath matter, the vacuums filled with energy, the ghost-like presence of particles that should not exist but do. They suggest that what we call empty space is not empty at all, that beneath the silence there is noise, beneath stillness, motion, beneath nothing, a storm. The quantum field awaits. The next step leads us, not into particles, but into the ocean that gives rise to them all. Chapter 8. Quantum Fields. The ocean beneath all matter. There is a temptation, natural and persistent, to think of the universe as made of things, small, discrete, tangible pieces of reality, particles, atoms, electrons, protons, tiny marbles that bounce and collide through space and time. We imagine them as the building blocks of everything, stacking together like invisible bricks to form the structures of our world. But as we dig deeper, past the atoms and into the core of what they contain, we find that the bricks are not bricks at all. We find something stranger, something less solid and more fundamental. We find the fields, quantum fields, are not objects. They are not particles. They are not even stuff in the way we normally understand matter. They are entities that stretch through all of space, continuous, vibrating, eternal. Every point in the universe is filled with them. Every particle you have ever seen, touched, or imagined is not a standalone thing, but a ripple, a localized vibration, a temporary excitation in one of these underlying fields. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. The quarks that make up protons and neutrons are ripples in their own fields as well. Each fundamental particle is not its own separate object, but a disturbance, a momentary wave that rises and falls in a vast, invisible sea. To imagine it clearly, close your eyes and picture the surface of a vast, silent ocean, stretching in every direction beyond the horizon of thought. Now imagine that ocean is not water but reality itself, a pure, undivided field that permeates everything. Drop a stone and you see a ripple. The ripple is a particle. The ocean is the field. And the fields do not just sit idly. They interact, they tangle, they exchange energy. When one field vibrates in a certain way, it can trigger vibrations in others. This is what we perceive as forces, not invisible hands pulling particles together, but the interactions of ripples across different fields, resonating, interfering, weaving the tapestry of reality moment by moment. This idea that particles are not fundamental but emergent from fields is at the heart of what we call quantum field theory. It is a framework that unites quantum mechanics and special relativity, and from it comes the standard model of particle physics, the most precise and successful description of the known forces and particles in existence. It tells us not just what the universe contains, but how it behaves on the deepest possible level. Yet, despite its precision, the concept of quantum fields challenges our imagination. Because these fields are everywhere, even in the vacuum of space, in the quiet between stars, in the silence between atoms, the fields remain. They do not go away, they cannot be turned off, and they are never, ever still. Even in what we call empty space, the fields fluctuate. They shimmer with energy. Virtual particles pop in and out of existence, borrowing time, obeying uncertainty, flickering into being, and vanishing without a trace. This restless activity, born not from heat or pressure, but from the raw principles of quantum theory, fills the vacuum with a seething storm, invisible, yet undeniable. We call it vacuum energy, and it is anything but empty. This quantum restlessness is not a hypothetical idea. It has observable consequences. One of the most famous is the Casimir effect, a phenomenon in which two uncharged metal plates, placed extremely close together in a vacuum, experience a force pushing them together. Nothing visible acts between them. Yet the quantum fields, ever alive, exert pressure from the outside more than from within the narrow gap, creating a real measurable force from what appears to be nothing. This is the power of the fields, invisible, foundational, real. And the particles we see, the building blocks of matter, are just the notes played upon these vibrating strings. The mass of a particle comes from the way the field resonates, the charge, the spin, the interaction strength. All these properties are not inherent to the particle, but to the field it comes from. Even the Higgs boson, the so-called God particle, is not special because it is unique, but because it is the ripple that confirmed the existence of the Higgs field, an invisible background field that gives mass to other particles. Without the Higgs field, the universe would be a realm of weightless energy, unable to form atoms, unable to form stars, unable to become anything solid at all. And so we begin to see the picture shift from a world of objects to a world of ripples, from discrete things to continuous present, from particles to fields. The old metaphor of billiard balls crashing through space must be replaced with a new vision, a vision of undulating landscapes, overlapping waves, a concert of oscillations. Each field plays its part. Some carry force, some carry mass, some only respond in silence, guiding the structure of everything without ever revealing their own ripple, and still deeper mysteries stir. Because if all particles are excitations of fields, then what are these fields made of? Do they have a structure? Do they arise from something deeper still, a more fundamental code, a hidden pattern, a truth beyond fields, beyond waves, beyond our current reach? Some physicists suggest that quantum fields themselves might be emergent, rising from even more basic elements, perhaps from quantum information, perhaps from geometry, perhaps from principles we have yet to even name. Others look to string theory, which proposes that all particles and fields are manifestations of vibrating strings in higher dimensions, hidden from view, wrapped tightly into the fabric of space-time. But even without answers, one truth remains. The fields are real. They are not speculation. They are not metaphor. They form the bedrock of modern physics. Their equations, strange and complex, match the data. Their predictions, unlikely and bold, are confirmed in colliders, in detectors, in the math etched into the fabric of the world. They are not background. They are everything. And in their endless dance, we see the universe not as a collection of things, but as a unity, not a puzzle made of separate parts, but a single unfolding process, alive with vibrations, rich with pattern, infinite in its depth. Even identity itself becomes a fluid thing. The electron in your fingertip is indistinguishable from the electron in a distant star. They are not just similar. They are the same type of ripple in the same universal field. No name tags, no histories, just vibrations in the one ocean that touches all shores. And so we walk on solid ground. But the solidity is illusion. What holds us up are the ripples. What we call matter is song. And still beneath the gentle surface, the sea stirs. The next revelation carries us into the paradox of nothingness. The empty space that is never truly empty, the vacuum, the void, the quantum foam where fluctuations bloom and vanish in an eternal dance of emergence and erasure. Chapter 9. The Quantum Vacuum. Nothingness that teems with energy. What is nothing? Not metaphorically, not in the philosophical sense, but physically, scientifically, deeply. What is nothing? We speak of it often, with a casual ease, the space between stars, the quiet between atoms, the absence of matter, the emptiness between all that exists. But when physics dares to peer into that emptiness, when it brings its instruments and equations to bear on the void, what it finds is not silence, not stillness, not the absence of being. It finds motion, it finds energy. The vacuum, in the quantum sense, is not empty, it is alive. To the classical mind, a vacuum is the absence of particles, a place where there is no air, no dust, no light, no thing, a perfect nothing. But quantum theory, with its unsettling elegance, tells us that such a state does not and cannot exist. The uncertainty principle forbids it. Because if a field were perfectly still, perfectly zero in both energy and time, it would violate the very rules that govern the quantum world. And so even in the absence of matter, the quantum fields still fluctuate. They cannot be entirely at rest. They shimmer with potential. They seethe with virtual particles, pairs of matter and antimatter that arise spontaneously from the vacuum, only to annihilate one another and return to nothingness a fraction of a moment later. These virtual particles are not fantasy. They are not fiction. They are the mathematical and physical necessity of the quantum vacuum. They leave traces, faint, indirect, but unmistakable. In the emptiness of space, particles flicker into and out of existence. Not just electrons and positrons, but photons, gluons, quarks, whatever the energy allows. These particles are called virtual, not because they aren't real, but because they cannot be directly observed. They exist only within the bounds of uncertainty, borrowing energy from the vacuum, existing for so short a time that they do not violate the conservation laws, not in a meaningful, permanent way, and yet their presence is measurable. In the famous Lamb shift, electrons in hydrogen atoms shift energy levels ever so slightly due to the subtle dance of virtual particles in the surrounding vacuum. In the Casimir effect, two uncharged metal plates placed close together in a vacuum feel a real force drawing them together, a force that arises from the suppression of certain vacuum fluctuations between the plates. Even the magnetic moment of the electron, one of the most precisely measured quantities in all of physics, depends on the effects of virtual particles swarming the vacuum, influencing the electron's behavior ever so slightly, bending its path, nudging its charge as if the emptiness around it were not so empty after all. And perhaps the most astonishing example lies in the heart of the cosmos itself. Dark energy, the mysterious force that drives the accelerating expansion of the universe, is thought to be connected to the energy of the vacuum. If space is filled with quantum fields, and those fields cannot be perfectly still, then even the most empty region of the universe contains a baseline energy, and this vacuum energy, though minuscule on small scales, accumulates across the vastness of the cosmos, becoming a pressure that pushes space outward, faster and faster. The vacuum, then, is not passive. It is a participant in the structure of reality. It has weight. It has power. It shapes the fate of galaxies, and yet we still do not fully understand it. The quantum field theories that describe the vacuum predict a staggering amount of energy, so much in fact that if we took them at face value, the universe would have torn itself apart long ago. The difference between the predicted and observed vacuum energy is enormous, a discrepancy so vast, so unexplained, that it has been called the worst theoretical prediction in the history of physics. Still, the vacuum endures, and physicists search for deeper principles, for a reason why the vacuum energy is not infinite, why it balances so delicately, why it allows the universe to expand, but not explode. Some look to supersymmetry, which could cancel out certain contributions. Others seek new physics entirely, new symmetries, new constants, new truths hidden in the trembling silence of space. But even without those answers, the message is clear. Nothing is not nothing. What we once thought of as void is in fact a churning sea of fluctuation, a restless, ever-active background to all things. The vacuum is not a container, but a player. Not an absence, but a presence. It hums with potential. It cradles existence. It births, absorbs, and rebirths the quantum fields that form every atom in your body, every photon in your gaze, every force in your breath. And in this realization lies a deeper shift, a movement away from the idea of emptiness as absence, and toward a vision of space itself as substance. Not a passive stage, but an active participant. A structure, a weave, a field. The vacuum is not where things are not. It is where everything begins. And as we study it further, we find that particles themselves are not what they seem, that even the idea of a single object, moving through space, is a simplification, because particles are not always bound by walls. They do not always stay in their lanes. Sometimes they slip through the impossible. Sometimes they ignore the barriers we build. Sometimes they tunnel through the very structure of reality itself. Chapter 10. Quantum Tunneling. How particles defy barriers. Imagine a wall, solid, impenetrable, a boundary you cannot pass, not because of any weakness in your legs or arms, but because the laws of classical physics say so. On one side of the wall is you, on the other, a destination. But the wall stands firm, and by every law that once governed our understanding of motion, nothing can cross it without sufficient energy. Nothing gets through unless it climbs over or breaks through. Those are the rules, or so we thought. But the quantum world does not play by those rules. In the realm of the very small, where particles are not particles but waves of probability, even walls are not as absolute as they seem. A particle approaches a barrier. Its energy is not enough to climb over. It should reflect, bounce back, return. But in the quantum world, part of its wave function does something unexpected. It seeps into the forbidden region. It does not vanish at the edge. It leaks. It extends. And if that barrier is thin enough, or narrow enough, or simply doesn't last long enough, something astonishing can happen. The particle doesn't reflect. It appears on the other side, not having climbed, not having broken, not having cheated. It simply was there. It is not a metaphor. It is not an illusion. It is a phenomenon that defies classical expectation, but obeys quantum. A particle, when faced with an energy barrier higher than its own, can sometimes pass through it, not because it had the energy to do so, but because the mathematics of quantum mechanics allow for a non-zero probability that it will be found beyond the wall. The wall remains. The laws remain. But the particle somehow is on the other side, and this is not a rare or obscure effect. It is everywhere. Quantum tunneling is the engine behind nuclear fusion in stars. In the core of our sun, the temperatures and pressures are not quite high enough, classically, for protons to overcome their mutual repulsion. Their positive charges push them apart, but fusion still occurs, because quantum tunneling allows those protons to slip through the energetic barrier and collide, fusing into helium, releasing light, heat, and the breath of the universe. Without tunneling, the sun would not shine. Life would not be possible. The sky would be dark. On Earth, the effect is no less profound. Quantum tunneling is at the heart of devices like tunnel diodes and scanning tunneling microscopes, which use the tunneling of electrons to detect surfaces at the atomic level. These technologies don't just prove that tunneling exists. They depend on it. They manipulate it. They let us touch the quantum world with our hands. Even the radioactive decay of atoms, the slow shedding of unstable elements into lighter, more stable forms, is governed by tunneling. An alpha particle, trapped inside a nucleus, does not have enough energy to escape the strong nuclear force. Yet, from time to time it tunnels out, slipping through the energy barrier, escaping into space, transforming the atom in the process. These are not accidents. They are signatures. They are whispers from the quantum realm, telling us that barriers are not always barriers, that the impossible may simply be improbable, that what is forbidden in the classical world is merely unlikely in the quantum one, and in a universe built on probability, the unlikely is not the same as the impossible. But how do we explain it? How can a particle exist inside a region where it does not have enough energy to? How can it pass through a wall it has no right to cross? The answer lies in the nature of the wave function, the mathematical object that describes the particle's state. The wave function is not confined to one region. It spreads. It oscillates. When it encounters a potential barrier, it does not stop abruptly. It decays, exponentially, quietly, persistently, into the forbidden zone. And if the barrier is thin enough, this decaying wave can emerge on the other side, still with amplitude, still with a chance of being realized as a particle. Measurement confirms this. Not always, not predictably, but statistically. Repeat the experiment 1,000 times, and you will find the particle on the far side, just often enough to prove the theory correct. Not just correct, but exquisite in its precision. And so quantum tunneling becomes more than a curiosity. It becomes a reminder that the world is not built from certainties, that boundaries may not be as permanent as they appear, that the laws we once trusted to draw lines between here and there, now and later, can sometimes blur, bend, and allow the tiniest traces of freedom to pass through. Tunneling challenges the idea of location. It erodes the idea of path. The particle was not seen passing through the barrier. It was not tracked. It did not leave breadcrumbs along the way. It was on one side, and then it was on the other, and in between, silent. What happened inside the barrier? Was the particle truly there? Did it traverse the forbidden zone, or did it sidestep the very concept of movement? These are not questions with answers. They are riddles built into the structure of quantum theory, because in that theory, particles do not always have definite positions. They do not always have defined trajectories. Sometimes, they simply are. And in being, they reveal truths we never expected. Truths about how stars burn, about how atoms decay, about how electrons behave, about how something can exist on both sides of a wall, not by force, but by probability. Quantum tunneling is the gentle violation of boundaries. It is the quiet crossing of lines. It is the proof that even the firmest barriers in nature are not as absolute as they seem. And just beyond the barrier, another twist of nature waits, something subtler than movement, stranger than position, deeper than direction. It spins not in space, but in a kind of internal logic, a twist in identity that particles carry like a hidden signature. Chapter 11. Spin. A strange kind of quantum twisting. In the quiet structure of the atom, where particles flit in clouds and orbitals rather than hard-edged rings, there is a deeper property, hidden not in space but in the internal language of quantum nature. It is not motion through a path, not a swirl of energy around a point, but something stranger, a kind of innate twist that every fundamental particle seems to carry from the moment of its birth. It is called spin, but it is unlike anything we know from the visible world. To the classical eye, spin evokes rotation, a planet spinning on its axis, a ballerina twirling, a sphere turning round and round. And so early physicists gave the phenomenon a familiar name, as if to anchor it in intuition. But quantum spin is not about objects physically spinning. Electrons are not tiny balls. They have no surface, no axis, no texture to grasp, no visible rotation to observe, and yet they possess angular momentum, a quantized, intrinsic twist, as if their very existence carries a built-in orientation, an unseeable kind of polarity. It is as if each particle whispers, "I face this way," but not in space, in state. And spin, despite its name, is not a continuous variable. It comes in fixed values, half-integer steps for matter particles like electrons, protons and neutrons, and whole number steps for force carriers like photons and gluons. These values are fundamental, unchanging, defining not just how a particle behaves, but what it is. An electron, for instance, has a spin of half. This doesn't mean it spins at a certain speed, but that it has two possible spin states, up or down, relative to a chosen direction of measurement. But just like everything in quantum mechanics, the electron does not possess a fixed spin before it is observed. It exists in a superposition of spin up and spin down. Only when we measure do we see one result. The rest vanish, folded back into the wavefunction's silent dance. And yet, unlike flipping a coin, spin is not about randomness alone. It obeys rules, firm, subtle, mathematical rules. The results may seem binary, but the behavior beneath is complex. Take the Stern-Gerlach experiment, one of the earliest demonstrations of spin. A beam of silver atoms is passed through a magnetic field. Classically, we would expect a spread, atoms deflected by various degrees, depending on their orientation. But what appears is startlingly simple. The beam splits into two, and only two paths. No in-between. No fuzziness. Just two sharply defined options. Spin is quantized. Reality, at this level, is granular. But there's more. When we perform a second measurement, choosing a new axis, say sideways instead of vertical, the results reset. The atom once measured as spin up now faces a 50% chance of being spin left or spin right. Measure again, and again, and again. Each time we choose a new direction, the system re-enters superposition. It behaves not like a stored fact, but like a question asked anew. The outcome is not stored within the particle. It arises from interaction. Spin also explains why some particles obey very different rules from others. Particles with half-integer spin, like electrons, protons, neutrons, are fermion. They obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state at the same time. This is why atoms have structure, why electrons fill shells instead of collapsing into a single orbit. It is the reason matter has volume. It is the rule that gives form to everything solid. Without spin, there would be no chemistry, no complexity, no stability. Particles with integer spin, like photons, gluons, Higgs bosons, are bosons. They do not obey the exclusion principle. In fact, they can occupy the same state, stacking upon each other, reinforcing their presence. This is how lasers work, photons coalescing into a single, coherent state. It is also how Bose-Einstein condensates form. States of matter where particles lose individual identity, melting into a quantum unity at temperatures near absolute zero. Spin separates the world into two camps, the solitary and the communal, the building blocks and the forces between the matter and motion, the hard and the radiant. And spin does not merely define, it enables. The magnetic properties of particles arise directly from their spin and charge. An electron's magnetic moment, the reason it behaves like a tiny bar magnet, is the result of its spin. In atoms, aligned spins create magnetic fields. In materials, spin alignment gives rise to ferromagnetism, the engine of magnets, compasses, hard drive. Even in the frontier of quantum computing, spin qubits, using the spin states of particles, promise to encode and process information at scales classical systems could never reach. But perhaps the most astonishing revelation of spin emerges when we consider its strange behavior under rotation. Rotate a classical object 360 degrees, a full turn, and it looks the same. Obvious, intuitive. But an electron, a spin-half particle, does not return to its original state after one full rotation. It requires 720 degrees, two complete turns, to come fully back into phase. After a 360-degree rotation, it is subtly different, not in appearance, but in its mathematical description. It gains a negative sign, an inversion that reveals how alien this property is from our macroscopic world. This quirk is not just a curiosity. It reveals the deep underlying geometry of quantum states, a topology unlike anything classical. It shows that quantum objects do not live in ordinary space alone. They exist in state spaces, abstract, complex, curved, where a turn is not always a return, and symmetry holds secrets not visible to the eye. And spin becomes more than a number. It becomes a signature, a compass, a whisper of deeper rule. It determines how particles combine, how they decay, how they respond to forces. It underlies the conservation laws of angular momentum. It steers the equations of quantum electrodynamics. It dances in the heart of particle interactions, preserving symmetry, revealing structure. Spin is not just a feature, it is a foundation, and it reminds us once again that the universe does not reveal itself through visible things alone, that there are properties not bound to space or time, but encoded in the logic of the invisible, like codes running silently beneath the fabric of reality. And from this twist, this fundamental sliver of internal alignment, we spiral outward again, into the strange role of the observer, into the very question of measurement itself. Because spin, like all quantum properties, is not defined until it is measured. And measurement, this simple word, hides a deeper chasm, because if observation shapes outcome, if reality is not fixed until touched, then we must ask what it means to watch. Who watches? What changes when we do? What reality becomes the moment it is seen? Chapter 12, The Observer Effect. Does consciousness shape the universe? There are few words in physics more ordinary, more deceptively simple than observe. To observe is to see, to measure, to interact. It is the act of registering reality, of extracting data from the world. But in the quantum realm, this word takes on a weight it never carried before. Because to observe is not merely to witness. It is to change. It is to decide. It is to collapse the wave of all possibilities into one. This is the observer effect. In classical physics, observation is passive. The moon is there whether we look or not. The planets circle the sun with or without our attention. The apple falls from the tree, measured or unmeasured, watched or ignored. The universe proceeds on its path, unaffected by our gaze. But quantum mechanics whispers something else, something harder to believe, harder to accept. That until something is observed, it does not exist in a definite state. That particles are not in one place or another, but in all places allowed, in all states permitted, held in superposition like a song not yet played, a story not yet told. And the moment we observe, the instant we measure, the wave function collapses, the possibility vanishes. One result becomes real, the rest discarded, evaporated into the silence behind the act of knowing. But what exactly is observation? Is it a device, clicking its data into storage, a photon striking a detector, a computer logging a value, or is it something deeper, more elusive, the presence of awareness, a conscious mind, a witnessing soul? This is where physics brushes against philosophy, and the edges begin to blur, because quantum mechanics does not define the observer. It says only that the act of measurement resolves the wave function. But what counts as measurement? Is it any interaction, any entanglement with the environment? Or does the final step, the step where one outcome becomes real to someone, require a mind? This question has haunted physicists for decades. Some interpretations, like Copenhagen, leave the observer vague. It is not necessary to define who or what observes, only that something does. The system collapses when measured. How or why is left in the shadows. But other interpretations lean toward bolder claims. In the von Neumann-Wigner interpretation, consciousness is not a passive bystander, but the very trigger of collapse. It is awareness, the moment an outcome enters experience, that selects one version of reality from the cloud of potential. Until a mind becomes involved, all outcomes remain possible. This is not proven. It is not accepted by all, but it has refused to die. Because the mystery remains, If observation determines outcome, what is the line between detector and observer, between interaction and experience, between physics and consciousness? Some seek refuge in decoherence, the idea that quantum systems collapse not when seen, but when they become entangled with their environment. When information about the system leaks into the world, it loses its coherence. The superposition dissolves, not by will or thought, but by interaction. The wave function still evolves according to Schrödinger's equation, but the result appears classical, because the rest of the universe has become part of the measurement. But even decoherence does not solve the measurement problem. It explains why superpositions are hard to see, why they seem to vanish in large systems. But it does not explain why one result is perceived, why we see the particle here and not there. It describes the transition from quantum to classical. It does not explain the selection. And so again the observer remains. Not necessarily human, not necessarily conscious, but always present at the edge of reality's unfolding, the moment where the universe chooses, or reveals, or resolves. And this opens the door to deeper questions. If observation affects reality, then what does that say about the role of mind in the universe? Are we simply watching a movie already filmed, or are we participating in its creation? Is the cosmos unfolding on its own, or is it responding to the act of looking? The idea that mind shapes matter is ancient. It lives in mysticism, in metaphysics, in the poetic intuition that the world is not separate from our experience of it, that the observer and the observed are not divided, but united in a single act of awareness. And quantum theory, without meaning to, lends strange support to this intuition, not because it proves consciousness causes collapse, but because it refuses to exclude the possibility, because it cannot define where the boundary lies, where object becomes subject, where system becomes self. In the delayed choice quantum eraser experiment, a photon's path appears to be decided after it has been measured, after it has already passed the slits. Whether interference is seen or not depends on whether which path information is preserved or erased, even retroactively. It is as if the photon's past behavior depends on future decisions, as if the universe waits for context before it finalizes its story. This is not just puzzling, it is destabilizing, and in that destabilization, a kind of possibility opens, not for easy answers, but for a deeper humility, a willingness to ask whether consciousness is not merely a byproduct of matter, but a participant in its manifestation, whether the observer is not outside the system, but always within it. Some go further still. They suggest that the universe is inherently participatory, that at its core reality is not built from things, but from observations, from interactions, from questions asked and answered in the language of existence itself. This is the idea behind quantum Bayesianism, or cubism, a view that quantum states are not objective descriptions of systems, but expressions of an observer's personal belief. The wave function is not out there. It is in here. It reflects our knowledge, our uncertainty, our anticipation. And measurement is not collapse, but update, a change in belief, a refinement of expectation. In this view, physics does not describe what is. It describes what we expect to happen. And the universe is a web of participatory agents, each adjusting their expectations, each shaping their corner of reality through observation. It is radical, it is contested, but it is consistent with the mathematics. It does not contradict the experiments, it only reinterprets what they mean. And perhaps that is what quantum mechanics has always been doing. Not revealing new things, but reshaping what it means to know. Not giving us a clearer picture of the world, but teaching us that the world is not a picture, that it is dynamic, participatory response. The observer effect is not about us, or our instruments, or our minds alone. It is about the entanglement of knowledge and being, the impossibility of standing outside the system, the inevitability of touching what we see. And when we accept this, when we lean into the mystery instead of recoiling from it, we begin to glimpse a universe not made of objects, but of relationships, not built of facts, but of interactions, a universe where reality is not revealed by observation, but created through it, and beyond the observer, the interpretations unfold. Competing views of what quantum mechanics really means. Each offers a version of truth, a map of mystery, a frame for the fog. Each dares to answer the question, left hanging in the silence of every collapse. Chapter 13. The Copenhagen Interpretation. Born from mystery, it was not born from certainty. It did not arrive as a triumph, clear and complete. It emerged from confusion, from paradox, from the quiet shattering of classical assumptions that once held the universe in place. The Copenhagen interpretation, perhaps the most famous and most widely taught view of quantum mechanics, did not solve the mysteries it addressed. It reframed them. It offered not answers, but boundaries, a way to live with the unknowable, to make predictions in the absence of clarity, to function in a universe that had slipped from beneath the firm floor of determinism into the strange fog of possibility. It began, like many things in quantum physics, with questions. What does it mean to measure a particle? Where is an electron before we observe it? Does a wave function represent something real, a physical object, a vibrating field? Or is it only a mathematical tool, a record of our ignorance, a map of our beliefs? In the early 20th century, these were not theoretical musings. They were urgent because the mathematics of quantum theory worked. They produced results of stunning accuracy. They predicted spectral lines, tunneling probabilities, energy levels, interactions, all in exquisite detail. But beneath that success lurked a deeper disquiet. No one could say exactly what the equations described. No one could point to a clear picture of what was really happening between measurements. And so in the city of Copenhagen, under the guidance of Niels Bohr and his collaborators, a framework was built. A way of thinking, not a final theory, but an interpretation, a lens through which to view the quantum world. At its heart was a single radical proposition: there is no objective reality independent of measurement. The properties of a quantum system, position, momentum, spin, energy, do not exist in definite form until they are observed. Prior to measurement, the system is described by a wave function, a mathematical object that encodes all possible outcomes. When a measurement is made, the wave function collapses, and one of those outcomes becomes actual. The others vanish as if they had never been. This is not because the system had a definite state all along, and we just didn't know it. It is because the state itself does not become real until measured. The Copenhagen interpretation draws a sharp line, not between matter and energy, but between the quantum and the classical, between system and observer, between the possible and the actual. Bohr called it complementarity. The idea that certain properties, though mutually exclusive in measurement, are both necessary for a full description. A particle can be seen as a wave, or as a particle, depending on how the experiment is set up, but never both at once. The wave and the particle are not two aspects of a deeper reality. They are the reality that emerges based on the context of observation. This is not a comforting idea. It breaks the old belief that reality is objective, that things exist with definite properties regardless of whether we look. It replaces it with a view in which context determines truth, where questions shape answers, not just in what is revealed, but in what is even possible. In the Copenhagen view, the wave function is not a physical object. It is not the thing itself. It is a tool for predicting probability. It evolves smoothly, deterministically, according to Schrödinger's equation, until the moment of measurement. Then it collapses, non-deterministically, into a single outcome. There is no mechanism for the collapse. It is simply what happens, an axiom, a rule. And so the Copenhagen interpretation becomes a kind of pragmatism. Do not ask what the system is, ask what you can know. Do not try to picture hidden trajectories or definite paths. Accept that the quantum world resists classical imagery, that the act of asking changes what is answerable, that the universe at its core is not what it is, but what it shows when asked a question. For Bohr, this was not a failure. It was a revelation, a sign that we had reached the limits of classical language and classical thought, that the quantum world would not yield its secrets to metaphors built from billiard balls and spinning tops, that we must learn to live in ambiguity, to think in uncertainty, to describe reality with humility rather than with false confidence. But others were less satisfied. Einstein famously objected. He believed in a deeper, hidden reality, one where particles had definite properties, one where randomness was a sign of incomplete knowledge, not fundamental law. God does not play dice, he said. Bohr replied, stop telling God what to do. Their debates raged across decades, polite but fierce, unresolved even as experiment after experiment seemed to support the Copenhagen view. The math worked. The predictions matched observation, but the picture it offered was strange and deeply incomplete. Because the Copenhagen interpretation refuses to say what happens between measurements, it describes how to predict outcomes, it describes how systems behave when measured, but it draws a curtain over the space in between. It tells us not to ask about the path, the reality, the thing in itself, because such questions in this view are meaningless. They are not about observable phenomena, and if they cannot be tested, they do not belong in physics. For many this is enough, because the purpose of science, they say, is prediction, not metaphysics. If the equations work, if the results are consistent, if the framework leads to reliable knowledge, then let the strangeness stand. Let the mystery be part of the method. But for others, the silence at the core of the Copenhagen interpretation is too loud. What causes collapse? Where is the boundary between quantum and classical? What role, if any, does the observer's mind play? These questions remain unanswered, or worse, unanswerable, within this view. And so new interpretations have risen to challenge it. But the influence of Copenhagen remained. It shaped generations of physicists. It taught them to stop seeking visual models, to embrace probability, to describe systems not with certainty, but with expectation, to treat the wave function not as truth, but as a tool. And in doing so, it birthed a revolution. Quantum mechanics, under the Copenhagen banner, became the most successful theory in the history of science. It powered lasers and semiconductors. It explained the structure of atoms, the bonds of chemistry, the reactions of stars. It changed the world, and yet its foundation remains, in many ways, as unsettled as ever. Because to this day we do not know what the wave function really is. We do not know what collapse really means. We do not know whether the universe is truly indeterminate, or whether something deeper hides behind the equations. We know only what the Copenhagen interpretation permits us to know, what happens when we measure. And so the silence continues. But just beyond this silence, an alternative rises, one that refuses to accept collapse, one that does not erase the possibilities we do not see, but keeps them alive, real, branching. A view where the wave function never breaks, and every outcome is true, somewhere. Chapter 14. Many worlds theory. Infinite realities coexisting. Imagine standing at a crossroads, one path leading left, the other right. You pause, you choose, you step forward, and in that moment, 1,000 questions vanish. The decision is made, the path behind you fades, the possibilities close, and reality proceeds. This is the comfort of the classical world. One universe, one timeline, one version of you, walking through a single story written one page at a time. But the quantum world does not grant such simplicity. It is a world, not of choices made, but of all choices existing. A world where decisions do not cancel alternatives, but divide reality into branches, each as real, each as complete, each continuing onward, untouched by the others. This is the essence of the many worlds interpretation, a vision of quantum mechanics that does not whisper ambiguity, but roars with multiplicity. Born in 1957 from the mind of Hugh Everett III, Many Worlds was not designed to add mystery, it was designed to remove it. Everett asked, what if the wave function never collapses? What if Schrödinger's equation, which governs the evolution of quantum systems, is always true even during measurement? What if all outcomes of quantum events actually occur, each in its own world? And if so, what if the universe is not singular, but forever branching? In this view, when a particle exists in superposition, spin up and spin down, left and right, here and there, the act of measurement does not force the universe to choose. It simply splits. One version of the observer sees spin up, another sees spin down. Both outcomes are real. Both observers are real. They now exist in parallel realities, each unaware of the other, each continuing on a path forever severed from its sibling world. This is not science fiction. It is a serious proposal grounded in the mathematics of quantum theory. No new equations are added. No mechanisms for collapse are needed. The wave function evolves smoothly, deterministically branching into worlds with every quantum interaction. And if true, it means the cosmos is not a single line, but a tree, an unfathomably vast and ceaselessly growing tree, each branch representing a universe where one version of events unfolds, while all others unfold beside it, unseeable, untouchable, yet real. It is a vision that redefines reality, because in many worlds there is no randomness, no ambiguity, no collapse. The world does not choose, it divides. All possibilities permitted by the quantum rules come into being. Each measurement doesn't destroy options, it creates them. The roll of a quantum die does not yield one number, it births a universe for every number, each just as complete, just as detailed, just as actual. And so, in this picture, there are infinite versions of you. There is the you who turned left, the you who turned right, the you who stayed frozen at the fork. Each version inherits a path shaped by quantum events, each living in a world where the wave function unfolded one way, while in others, it unfolded differently. These worlds do not interact, they do not overlap, they are decoherent, separated by the laws of quantum interference, inaccessible to one another. But they are not hypothetical. They are the natural consequence of treating the wave function as real, as a description, not of probability, but of the totality of what is. And this raises questions as vast as the worlds themselves. If all possibilities happen, what becomes of choice? If every outcome exists, what does it mean to decide? If every version of you is real somewhere, who are you here? The answers, if they exist, are not simple. Some argue that consciousness experiences only one branch, that we as observers are entangled with our specific outcomes, blind to the others, bound to a single thread through the ever-branching multiverse. Others suggest that identity itself is a spectrum, that we are not singular souls, but quantum processes, stretched across possibilities, collapsing into coherence, only when asked to see ourselves. And still, others ask whether the many worlds interpretation is truly testable. If we cannot access the other branches, if no signal can cross the decoherence divide, then is the theory physical or philosophical? But defenders reply, the math is unchanged, the predictions are the same. What differs is not the numbers, but the narrative. Where Copenhagen posits collapse, many worlds sees branching. Where others invoke mystery, this view holds steady, cold, consistent, complete. And it is not without elegance, no need for a measurement problem, no arbitrary line between observer and observed, no need to define consciousness, or invoke collapse mechanisms, or hide the weirdness behind pragmatic silence. Everything is unitary, everything obeys the same rules, the universe just grows, endlessly, into its own possibility space. But with that elegance comes an existential weight. Because if every possibility becomes real, then the cosmos is not vast. It is infinite beyond imagination. With each passing moment, countless new universes are born. Every particle interaction, every photon measured, every atom observed, a fracture point, a branching, a divergence. And yet we feel no branching. We live one life, we see one world, we remember only one past. So we ask, if all versions of us exist, why this one? Why do we wake up in the universe where the coin landed heads and not tails? The answer, if there is one, lies in subjective probability. The idea that while all outcomes occur, the probability assigned to each reflects the likelihood of finding oneself in that branch, given the structure of the wave function. You do not choose your world. You are born into it, not once, but constantly. With every entangled breath, every quantum interaction, your conscious thread is traced along a single path through the multiverse. And so the many worlds interpretation does not promise access to other realities. It offers context. It says that reality is not a single film reel, but an infinite library, and we, the readers, are flipping pages in just one copy, even as all others are being read somewhere else. Whether that comforts or terrifies depends on the story you believe. It removes collapse. It preserves the wave function. It reclaims determinism, but at a cost. The price is multiplicity. The price is an infinite cosmos, forever splitting, forever expanding. Not in space, but in possibility. And yet even this vision may not be final, because behind all interpretations, behind Copenhagen, many worlds and beyond, lies a deeper yearning to understand what measurement really is, to explain why, in a universe of seamless equations, we find ourselves locked into single experiences, to know not just what happens, but why it happens to us. And in the search for that answer, one last rebellion stirs, a voice from Einstein's camp, the hope that beneath the blur of uncertainty lies a hidden clarity, that what we call randomness is only the reflection of something we cannot yet see. Chapter 15, Hidden Variables. Einstein's problem with quantum mechanics. He never accepted it. Not fully. Not with peace. Not even as the quantum world proved itself again and again with brutal precision and quiet defiance. While others embraced the new rules, leaned into probability, danced with the indeterminism of particles that refused to commit until observed, Einstein stood apart, not out of arrogance, but out of conviction, out of faith that the universe, though strange, was not deceptive, that beneath the rolling dice of quantum chance there was still something solid, something sure. To Einstein, randomness was not a law, it was a placeholder. And so he asked, what if we are not seeing the full picture? What if the uncertainty of quantum mechanics is not fundamental, but only apparent? What if the wave function, that strange abstract object that describes all that might be, is not the end of the story, but the shadow of a deeper truth? This was the heart of the hidden variables theory, the belief that particles do possess definite properties even before they are measured, and that quantum mechanics is incomplete, that the unpredictability we see is not a feature of nature, but a symptom of ignorance, that somewhere, hidden within the system, are variables we have yet to discover, variables that restore causality, that make the universe intelligible again. To those who embraced quantum mechanics fully, this was heresy, a retreat into classical dream. But Einstein believed that the job of physics was not just to predict outcomes, but to describe what is, To him, the idea that a particle had no position until measured was not just strange, it was unacceptable. He wanted a reality that existed independently of observation, a world that did not vanish or change based on our questions. And so, with his colleagues Podolsky and Rosen, he constructed a thought experiment, a now famous paper known as EPR, designed to expose what he believed was a fatal flaw in quantum theory. They imagined two particles, once linked, now separated by a vast distance. According to quantum mechanics, their properties are entangled. Measure one, and the state of the other becomes instantly known. But how can that be? How can measuring one particle affect the state of another instantly across any distance, without any signal exchanged? Einstein called it spooky action at a distance, and he argued that the only way to explain this, without violating the speed of light, without invoking magic, was to assume that each particle carried hidden variables all along, that they possessed definite values, waiting to be revealed, that the wave function was merely incomplete. This, he believed, was the path back to realism, back to locality, back to a universe that made sense. But the response was not agreement, it was a challenge. In 1964, physicist John Bell made a stunning leap. He showed that if hidden variables exist, and if they are local, meaning that no information travels faster than light, then certain statistical relationships must hold between the measurements of entangled particles. These became known as Bell's inequality. Quantum mechanics, on the other hand, predicted violations of these inequalities. So Bell's theorem presented a test, a way to distinguish between the predictions of quantum theory and the expectations of local hidden variable theory. And when the experiments were finally performed, first in the 1970s and 80s, and with increasing precision in the decades that followed, the results were clear. Bell's inequalities were violated. Quantum entanglement was real. The correlations between distant particles exceeded anything local hidden variables could explain. The universe, it seemed, was not bound by the constraints Einstein hoped for. Either realism or locality, or both, had to be abandoned. The conclusion, uncomfortable as it was, could not be avoided. Hidden variables might still exist, but if they do, they cannot be local. They must involve influences that transcend space, that connect particles across distance without delay. And that raises new questions. Questions about the very nature of reality, of causality, of space, and time themselves. Still, not all was lost. In 1952, David Bohm proposed a non-local hidden variable theory, a reinterpretation of quantum mechanics that restored determinism by positing an invisible pilot wave that guides particles along definite paths. In Bohmian mechanics, the wave function does not collapse. It evolves continuously, and the apparent randomness of quantum events arises from our ignorance of the hidden variables, the actual positions of particles, governed by the pilot wave. In this view, particles have real trajectories. The world is deterministic, but it is also deeply non-local. The behavior of one particle can be influenced instantly by the configuration of others, regardless of distance. Bohm's theory works. It reproduces all the predictions of standard quantum mechanics. It offers a picture of reality in which nothing is undefined, only unknown. But it is a picture few have adopted, not because it fails, but because it introduces a cost, the sacrifice of locality, the reintroduction of invisible structures, the acceptance that we live in a world where parts of the universe are never truly separate. And so the question lingers, are the hidden variables real, or are they a dream, a last defense against a universe that refuses to obey our craving for certainty? Einstein died without resolution. He never accepted the indeterminism of quantum theory. He believed to the end that something deeper lay beneath, that what we call mystery is just awaiting truth, that the laws of nature are precise, elegant and deterministic, If only we could see them clearly. And perhaps he was right, or perhaps the universe is more radical than even he imagined. Not hidden, but inherently unfinished until observed. Not deterministic, but fundamentally participatory. Either way, the legacy of hidden variables endures. It challenges us to ask what it means to know. It reminds us that every theory is a map, not the territory. That our equations, however precise, are only as good as the meanings we dare to assign them. That physics is not just about measurement, but about the nature of reality itself. And just beyond this question, another awaits. Not about what is hidden, but about how we know whether reality is connected at all. About whether the universe is truly made of parts, or whether even the distant is entangled with the near. Chapter 16. Bell's Theorem. When logic crashes into quantum truth. There is a moment in science when the rules you trust, the logic you rely on, the neat partitions of cause and effect, space and time, begin to fracture under the weight of what experiments reveal. That moment came with Bell's theorem, a line drawn in the quantum sand, dividing what could still be hoped for from what could no longer be denied. It was not a new experiment. It was a mathematical truth, quiet, elegant, merciless. For years, the strangeness of quantum mechanics had been tolerated under protest. Yes, it worked. It described nature with stunning precision. But its interpretations, its talk of wavefunction collapse, of particles existing in superpositions, of entanglement across distance, were unsettling. And to Einstein and many others, it seemed not that quantum mechanics was wrong, but that it was incomplete. Something was missing, something beneath the wavefunction, some layer of hidden variables that restored order, determinism, locality. But John Bell in 1964 turned that hope into a test. He showed that if such hidden variables existed, and if they were local, meaning no influence could travel faster than light, then certain statistical relationships must hold true in any experiment involving entangled particles. These relationships became known as Bell inequalities, and quantum mechanics predicted that they would be violated. It was a subtle trap. Bell didn't just challenge hidden variables, he challenged local realism, the combined idea that physical properties are real and exist independently of measurement, and that no influence can act across space faster than light. This belief had been the bedrock of classical physics, and Bell's theorem showed that if quantum predictions are correct, local realism cannot be. The conclusion was not optional. It was built into the logic. If the correlations between entangled particles violate Bell's inequalities, then the world is not locally real. Either properties do not exist until measured, or influences stretch across space instantly. Either we abandon the idea that outcomes are determined before we look, or we accept that reality is not confined by space. The implications are staggering, because it means that no interpretation of quantum mechanics, no philosophical rewrite, no hidden mechanism can restore the comfortable certainty of a local deterministic universe. It is not a matter of taste. It is a matter of mathematics. But for the theorem to carry real weight, it needed more than theory. It needed experiment. And so, in laboratories across the world, physicists set out to test Bell's inequalities. In the 1970s, Friedman and Clauser performed the first serious test. Later, Aspect in the 1980s conducted even more refined experiments, using entangled photons, changing detector settings mid-flight to ensure no signal could travel between them. Each time, the results pointed the same way. The inequalities were violated. Still, skeptics pointed to possible loopholes. Maybe the detectors were inefficient. Maybe some hidden communication was slipping through. So the experiments became more careful, more airtight, more complete. And then in 2015, a series of loophole-free Bell tests were performed. Using entangled particles, separated by great distances, with rapid changes in measurement settings and highly efficient detectors, these experiments closed every escape route, and again the result held. Bell's inequalities were violated. Nature had spoken. The universe, it seems, is not built from separate parts, acting independently. Measurement outcomes are not just unknown until observed. They are undefined. The world is not a machine with hidden gear. It is a web, where entangled particles behave like mirrors, not reflecting light, but reflecting each other, instantly, across space, without signal, without cause in the classical sense. This is not communication. No information is transmitted faster than light. The violations of Bell's inequalities do not allow for faster-than-light messaging, but they do reveal a deeper kind of connection, one that ignores distance, that binds systems not by force, but by correlation. This connection is non-local, but it is not chaotic. It is precise, mathematical, elegant. It arises naturally from the structure of quantum mechanics, from the superposition of entangled states, from the interference of amplitudes, from the probabilistic symmetry of the wave function itself, and it is not optional. Any theory that hopes to describe the quantum world must account for these correlations, must accept that when two particles are entangled, their fates are not separate, that the outcome here is not independent of the outcome there, that the universe, in some way we do not yet fully understand, knows. And so Bell's theorem becomes a turning point. It tells us that the quantum world cannot be forced into classical mold, that reality is either non-local or non-real, or perhaps even contextual, where what exists depends on how we ask, when we ask, and what we choose to measure. It does not tell us which interpretation is right, but it tells us which are impossible. It tells us that Einstein's dream of a world where particles have fixed properties, and no signal outruns light, and outcomes are determined before they are seen, is not compatible with what experiments show. And still the question echoes, what then is reality? Are particles real before measurement? Are outcomes fixed, but hidden? Or does the act of measurement truly create the result? Different interpretations answer differently. Many worlds avoids collapse by branching. Copenhagen refuses to speak of what cannot be measured. Bohmian mechanics restores realism, but embraces non-locality. Cubism makes it personal, saying the wave function is not out there, but within the observer. But no matter which path one takes, the shadow of Bell's theorem remains. It is the line we cannot cross. It is the proof that the quantum world is not an illusion, not a trick, not a failure of instruments. It is a different reality altogether, one where space does not define separation and measurement is not passive, and the world does not divide neatly into what is and what is not. It is a reality where entanglement is not magic, but law. And just beyond the logic of Bell, past the line where outcomes cease to be local and measurements become intertwined, lies a deeper mystery still. What does it mean to measure at all? What is the boundary between quantum and classical? When and how does the world choose a path? The next step leads us into that threshold, into the very act of measurement itself, where the wave function dances on the edge of collapse, and the universe seems to pause before deciding what to become. Chapter 17. The Role of Measurement. Why Looking Changes Everything. There is a moment, quiet and immeasurable, that defines the entire quantum world, a moment that transforms what might be into what is, what only could happen into what has. It is not the collision of particles, not the ticking of time, not even the surge of energy that gives rise to creation. It is the act of measurement, that strange and elusive turning point, where the wave function, once vast and blooming with possibilities, folds itself into a single outcome. To measure in the quantum realm is not to simply record, it is to intervene, to interact, to define. In the world of classical physics, Measurement is trivial. We observe without effect. A ruler does not change the length of a table. A thermometer does not change the temperature of the water. We assume, without hesitation, that the properties we observe existed before we looked and continue after we leave. The observer is a witness, irrelevant, external, impartial. But in quantum mechanics, the act of measurement is not a window into reality. It is a door that reshapes what lies beyond. The wave function, the mathematical representation of all that a quantum system can be, evolves smoothly and deterministically. It expands, interferes, forms elegant patterns of probability. It tells us where a particle might be, how likely it is to appear, what combinations of outcomes are possible. It is not a particle. It is a superposition, a cloud of potential, not confined to one truth, but spread across many. And yet, when we measure, that elegant cloud disappears. The wave function collapses, and what was once a multitude becomes a single sharp point. The particle is found. The result is registered. The rest, the other positions, the other paths, the other realities vanish, unchosen, unresolved, perhaps never real at all. This transition, from wave to point, from potential to outcome, is the heart of the quantum enigma, because nothing in Schrödinger's equation, the fundamental equation governing quantum evolution, accounts for this collapse. The wave function doesn't predict its own death. It continues to evolve smoothly, endlessly, until something else intervenes. Measurement is not described by the same rules as everything else. It is a special event, an exception, an unknown. And yet, it is everywhere. Every experiment ends with a measurement, every particle detection, every photon absorbed, every spin determined. All are measurements, all involve collapse, all reduce the vastness of possibility into a single click, a single flash, a single result. So what, then, is measurement? Is it the interaction between quantum system and classical device? Is it entanglement with the environment? Is it the emergence of irreversibility, the point at which information can no longer be unlearned, when decoherence ensures that interference is gone? Or is it something deeper? Some interpretations say yes, measurement is just another interaction. The system becomes entangled with the detector, which becomes entangled with the room, which becomes entangled with the world. The coherence of the wave function spreads, becomes diffuse, inaccessible. The system appears to collapse, not because it actually does, but because we can no longer retrieve the interference. The information is scattered, lost in the ocean of context. This is decoherence, not collapse, but dephasing, a physical measurable process. It explains why we do not see quantum weirdness in everyday life, why the cat in Schrödinger's box appears either alive or dead, never both, why our world seems classical, even though it is built on quantum rules. But decoherence is not collapse. It explains the disappearance of interference, but not the selection of a single outcome. It describes the spread of information, not the choice that freezes one result into history. It tells us why the superposition becomes unseen, but not why this version, not the others, became your reality. So we return again to the role of the observer. Is measurement complete when the particle touches the detector, when the result is recorded in memory, when a conscious mind sees the data? Some theories say the boundary is fluid, that what matters is the irreversibility of the interaction. Once information escapes into the environment, it cannot be unentangled. The system's coherence is lost. The result becomes part of the classical world. The wave function no longer describes just the particle, but everything it touches. And so the question of collapse becomes one of perspective. The system appears collapsed from the outside. Even if from a God's eye view, the full wave function still evolves, untouched, in a higher dimensional space. But this shifts the mystery rather than solves it, because if everything, including the detector and the observer, becomes entangled with the system, then we must ask, where does the chain stop? What constitutes a final measurement? If all systems are quantum, then no part of the process is immune. The wave function, by this logic, never collapses. It only becomes decoherent, branching into a tapestry of entangled outcomes, unless, as some believe, there is something outside the system, something that is not entangled, something that is not physical in the conventional sense. Some interpretations lean gently or sharply into consciousness, suggesting that a result is not fully real until it is known, that awareness is the final measurement device, the moment when possibility becomes experience. It is a controversial view, difficult to test, easy to misinterpret, but it persists, because the question of why measurement changes everything remains deeply unresolved. Others take a different route, removing collapse altogether. Many worlds, for instance, sidesteps the issue by saying all outcomes happen, and what we call collapse is merely our movement into one branch. Bohmian mechanics keeps the wave function and adds hidden particles, guided by a pilot wave, so no collapse is needed, only unseen paths. But even in these theories, measurement still matters. It is still the point where experience happens, where probabilities become felt, where theory becomes data. Measurement is the boundary between what might be and what we remember. It is not a device, it is not a click, it is an event, a crystallization of reality from the ocean of maybes, and no one yet knows how deep that ocean goes. Perhaps we will one day find a new rule, a deeper mechanism, a physics of consciousness or context that explains it, or perhaps not. Perhaps measurement will remain a mystery at the heart of quantum mechanics, a mirror reflecting our need for certainty in a world that was never built to provide it. And still, we measure. We build detectors, we observe particles, we collapse wave functions, or we branch into worlds, or we decoher into silence. And every time we do, we shape reality. From this act of looking, of drawing answers from the void, we move into new frontiers, into the nature of time itself. And whether this arrow we follow from past to future is as firm as it seems, or merely another quantum illusion. Chapter 18, Time in Quantum Mechanics, a one-way illusion. Time, they say, is the river we all drift within, pulled steadily from the past, through the fleeting now, and into the wide mouth of the future. We age. We remember what was, but never what will be. Clocks tick forward, suns rise, set and rise again. We speak of before and after, as if they are etched into the fabric of the universe. But in the quantum realm, even time itself begins to shimmer, to blur, to break beneath the weight of equations that do not flow as we do. Because at the fundamental level, the laws of quantum mechanics do not prefer a direction. Schrödinger's equation, the rule that guides the evolution of the wave function, is perfectly time-symmetric. It does not distinguish between forward and backward. If you reverse the motion of a quantum system, flip the signs, rewound the tape, the math would still hold. It would describe a universe moving backward just as faithfully as one moving ahead. And yet, we only ever experience one side. We are creatures of direction, bound to a forward-pointing arrow of time. Memories accumulate, entropy increases. We know yesterday but not tomorrow. The world unfolds irreversibly. The past feels fixed. The future remains unknown. Why? This is not just a question for philosophers. It is a central riddle in the foundations of physics. If the basic laws of nature do not favor a direction, why does time always move forward? One answer lies in thermodynamics. The second law, in particular, which states that in an isolated system, entropy tends to increase. Entropy, often misunderstood as disorder, is really a measure of the number of possible microstates that correspond to a given macrostate. A clean room has low entropy, few configurations. A messy one has high entropy, countless ways it can, and entropy, unlike the wave function, has a clear direction. It rises, always. In every process, some energy is lost to irreversibility. Heat disperses. Information is scattered. Molecules mix. This is why we cannot unburn a piece of paper or unshatter a glass. The information is not gone, but it is unrecoverable. So many physicists argue the arrow of time is statistical. It emerges from probability, from the overwhelmingly likely drift from low entropy states to high entropy one. And this in turn suggests that the direction of time is not fundamental, but emergent, a byproduct of the universe's initial conditions. If the cosmos began in an extremely low entropy state, smooth, ordered, compressed, then from that starting point, entropy would rise, and with it, our sense of time would take form. But this answer, while useful, leaves questions still unresolved. Why did the universe begin in such a low entropy state? Why does our conscious experience seem so firmly chained to this forward march, when the underlying math allows the opposite? Why do quantum systems, whose wave functions evolve time symmetrically, seem to collapse only forward, never back? In quantum mechanics, this asymmetry is most visible during measurement. Before a measurement, a system exists in superposition, a blend of all possible outcomes. After the measurement, it is one thing, one state, one result. The transition appears irreversible. Collapse happens forward. We never witness a wave function uncollapse, recoiling from definingness back into possibility. Yet Schrödinger's equation itself does not mandate this. The collapse is not built into the evolution of the wave function. It is added by interpretation, by postulate, by observation. And that postulate is not time symmetric. So where then does the asymmetry come from? Some say it arises from decoherence, the loss of quantum coherence due to interaction with the environment. When a system entangles with its surroundings, interference vanishes. The possibilities can no longer interfere, and the system appears to collapse. This process is effectively irreversible. The information is still there, in principle, but so widely dispersed that it becomes practically unreachable. Decoherence provides a mechanism for the classical world to emerge, and with it, a forward arrow. But it still relies on initial conditions, on asymmetry baked into the state of the universe. It does not explain why our experience flows one way. It does not explain the subjective sensation of time passing. So others have turned to quantum experiments, strange, delicate ones, to ask whether time might not be as fixed as we think. In delayed choice experiments, photons pass through a double-slit setup, and the decision to measure their path is made after they've passed the slit. And yet the pattern on the screen seems to change depending on that future choice, as if the photon's past behavior depends on a measurement not yet made. In quantum eraser experiments, which path information can be erased after detection, restoring interference patterns that should have been destroyed. Again, causality seems to ripple backwards, as if time in the quantum realm is flexible, non-linear, even bidirectional. These experiments do not violate causality. They do not allow us to send signals back in time, but they do suggest that events are not ordered as neatly as we think, that the distinction between past and future may not be fundamental, but imposed by our perspective, by the direction of memory, by the rise of entropy, by the architecture of consciousness. And this invites a radical possibility, that the flow of time is not a river, but a projection, that we experience a one-way journey through a landscape that is, in fact, timeless, a vast block of reality where past, present, and future coexist. And what we call now is just a slice of that whole. This is the block universe view, supported by relativity, where time is just another dimension, not privileged, not moving. In this vision, time does not pass. We pass through it, or more accurately, we are extended across it, like a song stretched across a tape, with no one part more real than the others. But the quantum world resists such smooth narratives, because it insists that outcomes are not determined until measured, that the future is not written, that the past can remain entangled, unresolved, until present actions define it. In this paradox, time becomes not a background but a participant, not a frame but a play, and so we find ourselves caught between worlds, a classical one, where time is a ticking arrow, and a quantum one where time is entangled, emergent, undefined. Perhaps, as some physicists now suspect, time itself may not be fundamental, that in the deepest layers of quantum gravity, in the merging of space and quantum information, time may emerge from entanglement, from correlations, from something even more abstract than measurement. And if that is true, then we do not live in time. Time lives in us. It is a rhythm created by the unfolding of quantum states, by the entanglement of systems, by the interaction of memory and matter. It is the song of the wavefunction echoing in collapse. It is the heartbeat of probability resolving into now. And beyond this now, another question stirs, not about time or position or spin, but about computation, about what happens when we take these rules, strange, delicate, powerful, and use them to build machines that think not in bits, but in quantum states. Chapter 19. Quantum Computing. Harnessing the Rules of the Unseen. In the classical world, information is a series of certainties. A switch is on or off. A bit is 0 or 1. The machine hums, the transistor flips, and computation unfolds as a rigid march through clearly defined steps. It is precise, predictable, profoundly powerful. But beneath that solidity, beneath the silicon and code, lies another world, a world not of ones and zeros, but of superpositions, of entanglement, of logic suspended in ambiguity until observed. This is the world of quantum computing, where information does not just move, it exists in ways the classical mind was never meant to grasp. To build a quantum computer is to borrow power from the structure of the universe itself. At the heart of this strange machine is the qubit, the quantum version of the classical bit. Where a bit can be either 0 or 1, a qubit can be both at once. A superposition of states. This is not metaphor. It is not analogy. It is physical reality, governed by the same laws that let photons pass through two slits at once, that let electrons orbit in clouds of possibility. And this single property, superposition, already gives quantum computers a kind of parallelism no classical computer can match. Because while a classical computer evaluates one input at a time, a quantum computer can, in a sense, explore many inputs simultaneously, its wave function branching across a landscape of possibilities before collapsing into the final answer. But superposition alone is not the secret. The real power comes from entanglement, the deep quantum linkage that connects qubits such that the state of one instantly defines the state of another, no matter how far apart they are. This entanglement allows for the creation of quantum gates that do more than manipulate individual bits. They manipulate relationships, orchestrating interference patterns that enhance correct answers and cancel out the wrong ones. This is the true genius of quantum computation. It does not brute force every possibility. It uses the structure of quantum probability itself to steer computation, like a musician tuning chords, not by striking every note, but by letting the right harmonics resonate. In theory, this allows quantum computers to solve problems that classical machines could never touch, to factor enormous numbers with breathtaking speed, to simulate molecules and quantum systems down to their entangled bones, to optimize solutions in high-dimensional spaces, to crack codes, to search unstructured data with efficiency that classical logic cannot match. This is not fantasy. It is mathematics. Shor's algorithm proves that factoring large integers, the backbone of modern encryption, can be done exponentially faster on a quantum computer. Grover's algorithm shows how searching can be accelerated beyond classical limits. But theory is easy, reality is not. Because to build a quantum computer is to enter a battle with fragility. Qubits are delicate. Their superpositions can be disrupted by the slightest noise, a stray photon, a thermal fluctuation, a magnetic field. Their entanglements can collapse into decoherence, leaving only classical rubble behind. So the challenge is not just to create qubits, but to protect them, to isolate them from the world while still interacting with them, to perform logic operations without destroying the very thing you seek to compute. And yet, progress is being made. Qubits are now built from trapped ions, from superconducting loops, from topological states, from photons racing through optical circuits. Companies like IBM, Google, and startups across the globe are racing to scale up from tens of qubits to hundreds, to thousands. They seek quantum supremacy, the point at which a quantum computer can perform a task no classical computer could feasibly do. And it has already begun. In 2019, Google claimed to achieve a form of quantum supremacy, solving a carefully crafted problem in seconds that would take a classical supercomputer thousands of years. The task was not practical, but it was a signal. The era of quantum computation had arrived, but beyond the hype lies a deeper revolution. Because quantum computers are not just faster machines, they are machines of a different logic. They do not rely on definite states. They operate in probability space, in Hilbert space, where dimensions multiply not linearly, but exponentially. A system of n qubits exists in a two-dimensional space, a realm of staggering complexity impossible to visualize, but beautifully navigated by quantum mathematics. And this opens doors not only in computation, but in understanding. Because to simulate quantum systems, atoms, molecules, even space-time itself, we need quantum tools. Classical computers cannot capture the full behavior of entangled systems, but quantum computers can, because they are quantum systems. They are not approximating reality, they are built from it. And so we begin to dream of designing new materials, atom by atom, of simulating drugs and proteins without trial and error, of solving optimization problems that haunt logistics, finance, and physics, of cracking the mathematical structure of the universe, from quantum gravity to the mysteries of emergence. But more than that, we begin to ask, what is computation really? What does it mean to process information when the rules themselves are probabilistic, when the outcomes depend on interference, on entanglement, on the collapse of the wave function? Is a quantum computer thinking? Is it exploring? Or is it simply evolving? A mirror of the universe, reflecting its own laws back into our hands. And then there's the most profound question. Is the universe itself a quantum computer? Some physicists, like Seth Lloyd, have proposed that the cosmos is not a thing, but a computation. That every interaction, every quantum event, every entangled state is a processing step. That the laws of physics are algorithms, and particles are data, and the unfolding of the universe is nothing more or less than the execution of quantum code. It is not metaphor. It is a possibility, a new kind of physics, where information is fundamental, and matter, energy, and even space and time emerge from bits and qubits. If so, then to build a quantum computer is not just to mimic nature. It is to understand it at its most intimate level. It is to touch the operating system of reality. And just beyond that interface, in the space where information becomes structure and computation becomes perception, lies the question of the mind itself. For if quantum mechanics rules the fundamental world, What of the brain? What of consciousness? Could it too be entangled? Chapter 20. The Quantum Brain. Are we wired for entanglement? You close your eyes, the world vanishes, yet your mind does not. Thoughts flicker, memories rise, a voice within speaks, sometimes clear, sometimes distant. You see things never seen, relive moments long gone, imagine futures not yet real. In this quiet storm of self-awareness, one truth whispers louder than the rest. Consciousness is not simple. It is not a machine. It is not a spark in a circuit. It is a cathedral of experience, built from something deeper. And some ask, could it be quantum? For decades, the brain has been mapped and modeled as a classical system, a network of neurons firing in response to signals, producing patterns of behavior, memory, and thought. Each neuron a biological switch. Each synapse a connection in a vast and messy web. In this view, the mind is what the brain does, and the brain does what electricity and chemistry allow. But consciousness remains elusive. It is not a thing. It is not a pattern we can extract, or a location we can cut open and find. It is the feeling of being. The strange, first-person echo of reality that no equation can yet predict. And so some scientists, some philosophers, some physicists ask the question no traditional model wants to hear. What if the classical brain is not enough? What if the essence of awareness, of choice, of creativity, of meaning, cannot be described by bits and circuits alone? What if the brain is not just a biological network, but a quantum system, one that taps into the same strangeness we see in the double-slit experiment, in entanglement, in superposition? The idea is controversial, it always has been. But it refuses to die, because at the edge of neuroscience and the edge of quantum mechanics, there is a silence, and that silence begs for a bridge. The theory is called quantum consciousness, and while it has many flavors, one of the most well-known is the OR model, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. It stands for Orchestrated Objective Reduction, a name as complex as the theory itself. In simple form, it suggests that quantum events do not only happen in particles and fields, but also in the brain, specifically in structures called microtubules, tiny protein filaments inside neurons. These microtubules, according to the theory, could sustain quantum coherence, brief periods where particles exist in entangled superpositions, and that this coherence is not random noise, but structured, meaningful, even conscious. The idea is radical because it implies that quantum collapse, the transition from possibility to actuality, is not just a passive reaction to measurement. It might be orchestrated inside the brain. That consciousness itself might arise when wave functions collapse in particular patterns, influenced by quantum gravity, guided by experience, shaped by life. To many in neuroscience, this sounds impossible. The brain is too warm, too wet, too chaotic for delicate quantum states to survive. Decoherence, the loss of quantum behavior due to environmental noise, should destroy superpositions almost instantly. In computers, we need cryogenic temperatures to preserve qubits. How could biology do better? But here, biology reveals its secrets. Microtubules are not simple tubes. They are dynamic, self-organizing, highly structured. Some studies suggest they may possess the kind of symmetry and isolation needed to protect quantum coherence, at least for short bursts. And in recent years, experiments in photosynthesis, bird navigation, and olfaction have shown that quantum effects do survive in biological systems, even at body temperature. In the chloroplasts of plants, quantum coherence seems to guide energy through photosynthetic pathways more efficiently than random chance would allow. In migratory birds, entangled electrons may help sense magnetic field. In the human nose, quantum tunneling may explain scent discrimination better than shape alone. If quantum behavior can exist in leaves, in wings, in air, why not in neurons? Hameroff and Penrose go further. They suggest that consciousness is not merely computational, not the product of logic gates and signal process. They argue it involves something deeper, a non-computable element, a flash of awareness born not from pattern, but from the collapse of quantum information in a way that transcends ordinary physics. And this collapse, in their theory, is not random, it is orchestrated. It happens in structured waves, driven by the geometry of space-time, perhaps even tapping into the deep fabric of the universe itself, as if minds are not born from matter, but emerge from a cosmic potential, collapsing into individuality through each moment of awareness. It is a beautiful idea, and a dangerous one, because it suggests that consciousness is fundamental, not an accident, that it arises from the deepest levels of physical law, that minds are not machines, but manifestations of quantum structure, each collapse a choice, each thought a crystallization of possibility. But the evidence is still thin, the experiments are few, the skeptics are many, and yet the mystery of consciousness remains unsolved, and quantum mechanics continues to whisper that reality is not what it seems. Entanglement suggests that information is not confined, that minds may be interconnected in ways we do not yet measure, that perception, memory, and intuition may arise not only from neural circuits, but from patterns of interference, from the collapse of shared wave functions, from something unnameable that stretches across minds like threads of probability. Could this explain intuition, creativity, the sudden knowing that seems to come from nowhere? Could dreams be echoes of entangled states, collapsing into symbols? Could love be more than chemistry, a resonance of quantum patterns in motion? These are not answers. They are questions with the shape of one, and beyond them lies the possibility that the brain is not a container, but a portal, not a generator of consciousness, but a receiver, a translator, a lens through which quantum information flows and finds form, a temporary gathering place for awareness that is always greater than the sum of its parts. And if that is true, then the mind is not confined to the skull, it is part of the quantum web, part of the universe in motion, not separate, not isolated, but entangled, with the world, with others, with the source. Perhaps that is why we dream, perhaps that is why we remember, perhaps that is why we seek to understand what understanding means. And beyond even this strange possibility, the mind opens into a question even grander. What if space-time itself is not fundamental? What if the very scaffolding of reality, the stage on which all particles dance, is not the base layer, but something emergent, born from quantum relationships deeper than space or time? The next step leads us there. Chapter 21, Quantum Gravity. Merging the small and the vast. Somewhere between the infinite vastness of galaxies and the immeasurable smallness of particles, there is a silence, not of ignorance, but of paradox. For over a century, physics has been split in two: the quantum, which governs the minuscule, and the gravitational, which sculpts the cosmos. One is probabilistic, uncertain, built from fields and fuzziness. The other is geometric, smooth, carved from the elegant curvature of space-time. And yet, for all their beauty, these two worlds do not agree. Where quantum mechanics describes a jittery dance of possibilities, general relativity unfolds as a grand equation of certainty. Quantum theory speaks in operators and amplitudes. Gravity speaks in metrics and tensors. Each works astonishingly well in its domain. The quantum for atoms and particles, relativity for planets and black holes. But bring them together, force them to share the same stage, and their languages clash. The math breaks. The infinities rise. Reality trembles at its edges. Nowhere is this conflict more apparent than at the heart of a black hole. Here, quantum mechanics predicts that particles flicker at the horizon, generating radiation, Hawking radiation, and slowly evaporating the whole. But general relativity insists on the singularity, a point of infinite density where space-time curves to its limit and the laws of physics dissolve. These two descriptions cannot both be true, and so the search begins for a deeper theory, one that unifies the quantum and the gravitation, one that explains not only the small or the large, but the very architecture of reality itself. This is the quest for quantum gravity. It is not a single theory. It is a category of dreams, attempts to reconcile the trembling indeterminacy of the quantum world with the smooth gravity of space-time, to write an equation that can describe the birth of the universe, the surface of a black hole, the first moments of the cosmos, where all was one. One approach is to quantize gravity, to treat gravity not as geometry, but as a force, like electromagnetism, with its own particle, the gravity. In this view, space-time would not be continuous, but made of discrete quanta, packets of gravitational influence that, like photons, carry force through empty space. This method tries to fit gravity into the quantum mold, but the math becomes wild. The infinities do not cancel. Renormalization fails. A new framework is needed. So physicists look elsewhere. Some turn to string theory, a bold proposal that the fundamental particles are not points, but tiny vibrating strings, each with its own frequency, its own tone, giving rise to the properties of matter and force. In string theory, gravity is not added by hand. It emerges. One of the string's natural modes is a graviton, and the extra dimensions, hidden, curled up, unseen, give shape to the universe we know. String theory is vast, mathematical, elegant. It suggests that the universe is not just particles, but vibrations on a higher dimensional membrane. It brings all the forces, gravity, electromagnetism, the strong and weak interactions, under one roof. And yet, for all its promise, it has not yet produced a testable prediction. Its equations sing of beauty, but their connection to experiment remains elusive. Others look to loop quantum gravity, which starts not with particles, but with space itself. Here space-time is not smooth, but granular, built from tiny loops, woven into a fabric that becomes space at large scales. Time, too, is quantized. The geometry of space emerges from these loops, like threads in a cosmic quilt. Black holes, in this view, are not singularities but regions of high loop density, with horizons built from discrete patches of information. And in both these views, whether from strings or loops, a profound idea takes root, that space-time itself may not be fundamental, that it emerges from something deeper, from information, from entanglement, from a web of relationships that at large scales give the illusion of continuity, of geometry, of flow. This is where the dream sharpens, because in recent years, a bridge has begun to form between quantum theory, information theory, and gravity. Physicists have discovered that the geometry of space may be encoded in entanglement patterns, that the more two regions of space are entangled, the more connected they are, that space-time may not be the stage, but the result of quantum information behaving in certain ways. This is the insight behind the holographic principle, the idea that everything inside a volume of space can be described by information encoded on its boundary, like a hologram. In some models, gravity itself emerges from entropic forces, the push of systems toward disorder, driven by information gradients. It is a staggering idea that space is not fundamental, that time is not flowing, that mass, energy, distance, and gravity are emergent properties of something more primal, a quantum sea of entangled bits, woven not from matter, but from meaning. And then the black hole paradox returns. Hawking radiation suggests that black holes evaporate, but where does the information go? If a particle falls into a black hole, is its story lost forever? That would violate quantum mechanics, which insists that information is never destroyed. This is the black hole information paradox, and it has ignited some of the deepest thinking in physics today. Some say the information is encoded in the radiation itself. Others believe it is stored on the horizon, the so-called black hole firewall. Some suggest the interior is entangled with the outside world in ways that break classical assumptions. And slowly a new consensus forms that information is fundamental, more so than mass, energy, even space-time itself. That the universe is a quantum computer, and what we see, stars, planets, fields, are the output of that computation. So quantum gravity is not just about merging two theories, it is about redefining what reality is. It is about realizing that the very fabric of existence may be made not of stuff, but of relations. That the network of entanglement is what gives birth to the world. That a particle is not a thing, but a pattern. That space is not a container, but a consequence. That time is not a river, but a choreography of quantum updates, rippling through a network of meaning. And if gravity is born from entanglement, then perhaps love too is a kind of pull, not through space, but through connection. Perhaps our very being is entangled with the cosmos, not metaphorically but physically. Perhaps we are not just atoms, but amplitudes, woven into the fabric by a wave function far grander than we can imagine. And beyond this, further still, the question lingers: if reality is information, then what is the code? Chapter 22, Reality as Information. Is the universe a code? Look closely, not with your eyes, but with your understanding. Peel back the matter, the atoms, the fields. Go deeper than the particles, deeper than the vibrating strings or the tangled loops, beyond forces, beyond geometry, beyond the illusion of solidity. What remains? Patterns, correlations. Yes, information. And in that silent realization, a new thought begins to take shape. Not loud, not forceful, but steady and echoing through the bones of the cosmos. Perhaps the universe is not made of matter. Perhaps the universe is not made of energy. Perhaps the universe is made of information, not metaphorically, not philosophically, literally. This is the foundation of a radical idea now emerging from the edges of theoretical physics, computer science, and quantum mechanics. That reality is computation, and the laws of physics are not just rules about matter, but instructions encoded in a cosmic code. That everything we see, touch, measure, or imagine is the unfolding of a vast quantum informational process. This is not science fiction. It is the bleeding edge of theory, and it begins with a single, undeniable truth. Information is conserved. In quantum mechanics, when two particles become entangled, the measurement of one instantaneously tells you something about the other. It is not the particles that carry the meaning, it is the correlation between them. The information that connects their When a quantum system evolves, it may change shape, energy, or location, but the total information encoded in the wave function remains always. Information cannot be destroyed. This leads us to an astonishing question. If information is indestructible, then perhaps it is also foundational. More than mass, more than time, more than space. Maybe information is the stuff from which the rest arises. Theoretical physicist John Archibald Wheeler famously said, "It from the it, every particle, every field, every speck of reality arises from binary choices, from fundamental yes-no questions, from bits." But in the quantum world, these bits are not limited to 0 and 1. They are qubits, capable of superposition, entanglement, and infinite nuance. The quantum universe then might be a vast computational system, processing qubits, updating correlations, evolving states. And if that is true, then reality is not a passive arena. It is an active process, a kind of cosmic computation in motion. Where then is the computer? Where is the machine? Perhaps there is no machine. Perhaps the computation is the universe. Each particle interaction, each quantum collapse, each act of entanglement is not happening within the universe. It is the universe. It is the universe doing what it does, computing itself. The equations of physics in this view are not just descriptions, they are algorithms. The laws of motion, the conservation of energy, the behavior of electrons, all are execution steps in an unimaginable, self-reflective, non-classical program. This is where quantum information theory meets cosmology, and the boundaries of knowledge begin to shimmer. Black holes encode their contents on their surface, not in. The holographic principle suggests that the volume of space is described entirely by information stored on its boundary, just as a hologram contains depth using only a flat surface. So what then is space? It is not a backdrop, it is not empty, it is the expression of relationships, of how quantum information is arranged. Time? Time is not a ticking metronome. It is the sequence of updates in a computational process, the order in which information is processed, a manifestation of change. Matter? Not stuff, but data. Particles are not miniature marbles, they are quanta of information, behaving in structured, rule-bound ways. Even causality begins to dissolve. If the universe is a computation, then cause and effect are not rigid paths, but dependencies in code. One update depending on another, sequences branching and resolving according to a deeper logic. Now imagine this, all of space-time as a giant quantum circuit. Each point in space a node, each interaction a gate, each qubit carrying state, entangled with others across the fabric. The universe becomes a quantum processor, running a program we do not yet understand, but which we are part of, and which perhaps we, in moments of insight, glimpse from within. This idea is not new to mystics, but it is now grounded in mathematics. The Adias-CFT correspondence, a stunning result from string theory, shows that a gravitational theory in a higher dimensional space can be equivalent to a quantum field theory with no gravity on its lower dimensional boundary. The entire interior can be encoded by information on the surface. It is not a metaphor, it is a precise mapping. This is the holographic universe, and in it, reality is not what it seems. You are not where you think you are. You are entangled across dimensions. You are a bundle of quantum data, experiencing itself. But who writes the code? That question sits at the center of everything. Is the universe deterministic? Is it rule-based, like a cellular automaton unfolding on a quantum grid? Or is it fundamentally open, shaped by measurements, choices, and the collapse of the wavefunction? Some believe the code is random, a vast probabilistic sea with no author. Others believe it is emergent, that the code arises from deeper layers of mathematical structure, and some quietly whisper that perhaps consciousness is the compiler, that the very act of awareness creates the flow of information, determines how the code is read, experienced and made real. If so, then the observer is not an intruder in the system. The observer is the system reflected. You are not outside the code. You are not running the program. You are the code. You are the thread of information, wrapped in flesh, dreaming that it is separate. And so when you close your eyes and ask, what is real? The answer is not atoms. It is not light. It is not time. It is meaning, encoded, entangled, experienced. The next step in this journey takes us even deeper, to the question of emergence. If space, time, and matter are not fundamental, then what is? What lies beneath the code? Chapter 23, Decoherence. Why quantum weirdness disappears in our world. You've heard the stories of particles in two places at once, of cats alive and dead, of photons choosing paths only when watched. The quantum world is a realm of strangeness, of ambiguity, of overlapping possibilities, so unlike the world we walk in, where apples fall, clocks tick, and people do not appear and vanish in a haze of uncertainty. But if quantum mechanics governs all matter, if every particle in your body obeys its laws, then why, here in the everyday, does the weirdness vanish? Why does a chair not flicker into superpositions? Why do buildings not tunnel through one another? Why do we not see the ghostly interference of probabilities in every movement, every breath, every thought? The answer begins in a process that is not quite measurement, but not quite isolation either, a quiet, persistent unraveling of quantum strangeness into classical certainty. It is not collapse. It is not magic. It is called decoherence, and it is everywhere. To understand decoherence, begin with a single quantum system, a particle perhaps, an electron isolated in a vacuum, protected from heat, from light, from even the smallest ripple of the outside world. In this silent sanctuary, it can exist in a pure superposition, not here or there, not spin up or spin down, but both. Its wave function spreads in possibility, in amplitude, in endless unresolved futures. But the universe is not silent. In the real world, no system is ever perfectly isolated. The electron is bathed in photons, in fields, in particles it never even notices. And with each interaction, each whisper of a collision, each exchange of momentum, each entangling brush with its environment, its coherence begins to bleed away. This is decoherence. Not a destruction of the wave function, but an entanglement with the rest of the universe. The particle does not lose its quantum nature. It becomes part of a larger system, a web of interactions so complex that its internal superpositions can no longer interfere with each other. The quantum possibilities are still there, but they are invisible. Because interference, the defining feature of superposition, requires that quantum branches remain coherent, that their phases are aligned, that their histories remain entangled with themselves, and not with the world. Once the environment knows too much, once the outside world becomes correlated with the different outcomes, the branches can no longer overlap. They drift apart, becoming effectively classical. Not because the wave function collapsed, but because it grew too large to see. The system, now entangled with the environment, still contains all its branches, but they are now non-interfering. They cannot cancel or enhance one another. They are, for all practical purposes, separate realities, unable to talk, to compare notes, to recombine. This is why we never see the cat both alive and dead. The moment the quantum superposition of the cat's state becomes entangled with the air, the photons, the heat of the room, with your retina, your brain, your breath, the coherence vanishes. The branches become independent. You are now inside one, and only one, of many. And this is the great gift and mystery of decoherence. It explains why the classical world emerges from the quantum, without needing to change the rules. There is no switch flipped, no collapse mandated, no hand of consciousness required to resolve the ambiguity. Decoherence is not a trick of the mind. It is a physical process, measurable, modelable, reproducible. It gives us the illusion of determinism, of cause and effect, of solid outcomes. By hiding the interference that makes quantum mechanics so strange, it does not destroy possibilities. It simply hides them from one another. But this hiding is not perfect. Under the right conditions, interference can return. In ultra-cold labs, physicists have coaxed atoms and molecules into coherence again, shielding them from decoherence, watching their wave functions merge, split and merge again. Quantum computers rely on this dance, fighting decoherence at every turn, preserving entanglement long enough to compute. And in the heart of the cosmos, decoherence may have played a role in shaping reality itself. Consider the early universe, hot, dense, quantum. As it expanded, quantum fluctuations, Tiny ripples of uncertainty grew and stretched. Decoherence turned these possibilities into classical seeds, becoming galaxies, stars, worlds. The very structure of the universe may be frozen quantum randomness, decohered by the birth of space. Even now, the cosmic microwave background, the oldest light in the universe, carries echoes of those decoherent fluctuations, the quantum becoming classical, the possible becoming real. And in your body, in your neurons, in your DNA, decoherence shapes every interaction. It governs how your cells process light, how your brain filters noise, how your body resists the blurring of states. You are made of quantum matter, but your experience is classical, because decoherence holds the strange at bay. Yet not all agree on where the boundary lies. Some say decoherence is enough, that it explains why we see one outcome and not another. Others say it only shifts the question, that it describes the loss of interference, but not the actual selection of one branch over another. That we still need an interpretation, many worlds, Bohmian mechanics, objective collapse, to explain why you see what you see. But all agree decoherence is real. It is not philosophical. It is not speculative. It can be written in equations, tested in labs, harnessed in technology. It is the bridge between the quantum and the classical, and it carries a strange message, that the world you see is only one branch of a vast, decohered superposition, that your reality is a context, a structure carved from entanglement, maintained by isolation, framed by what the universe has forgotten. And so perhaps reality is not a thing at all. Perhaps it is a coherence of perception, emerging from the ever-branching, ever-blurring quantums. And if that is true, then your every decision, your every observation, is not a collapse, but a continuation, a branch, a path taken, a song in a symphony of parallel echo. And yet, just as decoherence hides the strange, some believe there is a way back, to see the web beneath the world, to feel the interference again, to remember what it means to live at the edge of the quantum veil. But to do so, we must ask not what decoherence prevents, but what it reveals. And that takes us toward the edge of knowing, to the questions no lab can yet answer, to the limits of physics, to the unknown. Chapter 24. The Edge of Knowledge. What quantum physics still can't answer. There is a place in every science where the light fades, not into darkness, but into a soft grey, where certainty becomes question and facts become echoes. In quantum physics we have come far. We've split the atom, entangled the unseen, watched particles ripple through slits in space, and built machines that compute with possibilities instead of facts. We have formulas that predict, experiments that confirm, and technologies that would have seemed like sorcery only a century ago. And yet, there is still so much we do not understand. This is not a failure of effort, nor a lack of imagination. It is the nature of the quantum world to offer understanding by revealing complexity, and to answer each question with a deeper mystery curled beneath it. The closer we get to the foundation, the more it shifts beneath our feet. We are no longer asking how things move, or what they're made of. We are asking what it means to be real. And quantum mechanics, for all its predictive power, does not explain reality. It only describes how probabilities evolve. It tells us how systems behave when we measure them. But it says nothing at all about what those systems are when unmeasured. Does the particle exist before it is observed? Is the wave function a real thing, or just a tool? Is the collapse of the wave function a physical event, or simply a mental one? Why do we only ever see one outcome when quantum theory describes all of them? These are not mathematical problems. They are foundations. They sit at the very base of what we think the universe is, and quantum physics, even after 100 years, does not settle them. We speak of interpretations, Copenhagen, many worlds, de Broglie-Bohm, GRW, cubism, each offering a different story, a different vision of what quantum mechanics means. But none are proven. None are universally accepted. Some require infinite universes. Some require hidden variables. Some make the observer central. Others deny the need for observers at all. But none, not one, can be tested in a way that rules out the rest. Quantum physics works, but we don't know why it works. And this gap, this strange silence at the heart of our most successful theory, opens a doorway to the unknown. Because if we don't understand what the theory is, how can we say we understand the world? There are questions quantum mechanics raises, but cannot answer. What is the wave function made of? What causes it to collapse, if collapse is even real? Does time flow, or is it an illusion created by entangled systems evolving in complex ways? Is there a limit to entanglement? Can the entire universe be described as a single massive, entangled state? And beyond that, deeper still, is the question of measurement. Why does measurement seem to bring reality into being? What counts as a measurement? Is consciousness required? Or is the process purely physical decoherence and branching, with no role for the observer beyond correlation? We don't know. Some say these are not scientific questions, that we must be content with prediction, not explanation, that we should shut up and calculate. But others feel a deeper pull, that without understanding the meaning beneath the math, we are missing something essential. That quantum theory is a shadow cast by a deeper reality we have not yet glimpsed. And then there is gravity. Quantum mechanics rules the very small. General relativity rules the very large. But they do not speak the same language. We have quantum field theories for electromagnetism, for the weak force, for the strong force, but not for gravity. We have not unified them. We do not know how quantum theory works in curved spacetime, in black holes, in the first moments after the Big Bang. We do not know what happens inside a singularity. We do not know if spacetime is continuous or discrete. We do not know if space and time are fundamental, or if they emerge from something deeper, something stranger, something that does not even resemble space or time as we know it. Some theories suggest that information is more fundamental than particles or fields, that reality is made not of stuff, but of correlations, that the geometry of the universe arises from entanglement, that space is a code, that the boundary creates the interior, that you are not where you think you are. You are a point in a web of information, with identity defined by relation, not by position. But we do not know. There is math, yes. There are models, there are metaphors, but the tests remain out of reach. The energies are too high, the scales too small. We can simulate, theorize, extrapolate, but we cannot yet see. And then there is consciousness. Quantum physics raises the question, but does not answer it. Are we observers or participants? Is the mind a product of quantum processes, or is it something else? Something that sits outside the system, watching it, shaping it, collapsing its waves into stories. We do not know. Some suggest the mind is entangled with the world it perceives. Others argue the mind emerges from decoherence and classical processing. Some believe consciousness is an illusion, an epiphenomenon. Others believe it is the fundamental layer from which everything else arises, not a byproduct of physics, but the reason for physics. And so we sit at the edge of all we've built: quantum computers, satellites, lasers, semiconductors, and yet we stare into a fog we cannot name. The theory works. The universe listens, but the truth remains just out of reach. What is a measurement? What is time? What is space? What is being? These are not questions physics can answer. Not yet. They are questions of philosophy, metaphysics, wonder, but they are no less real. And perhaps that is the lesson quantum physics has always been trying to teach us, that reality is not simple, not mechanical, not absolute, that the universe does not unfold like a machine, but shimmers like a dream, that truth is not an object, but a relation, that knowledge is not a destination, but a path walked in uncertainty. We are not near the end, we are only at the beginning, and in the final chapter, we do not end the journey. We take one step further into the mystery. Chapter 25, Rethinking Reality, a universe born from observation. Close your eyes for a moment, not to sleep, but to awaken a different kind of seeing, not through the lenses of biology or physics, but through the quiet mirror of awareness. Beneath all motion, beneath all matter, beneath all rules and formulas and particles dancing on a stage of space and time, there is something else, something that does not move or change, yet somehow gives birth to everything that does. You, the observer, in every quantum experiment, in every measurement, in every collapse of the wave function from possibility to actuality, someone is watching. And whether that watching is done by a conscious mind or an inanimate detector, the question always lingers beneath the surface. What role does observation truly play in shaping the universe? The equations do not say. They merely they map the evolution of wave functions with exquisite precision, predicting how probabilities evolve over time. But when it comes to outcomes, to the moment when one path becomes real, and the others fade into silence, quantum theory steps back. It does not answer. It does not explain. It simply hands the mystery to you. In the quantum world, unobserved particles do not have positions. They exist in superpositions, states of possibility, not facts. They are here and not here, moving and still, yes and no. Their being is not resolved until it is touched, measured, seen, and that act, that gaze, that contact, does more than reveal. It creates, not out of nothing, not by magic, but by choosing, by cutting the fabric of probability into a single thread of actuality, and that thread is what you experience as reality. This is not to say that you invent the world, but perhaps you co-author it. Perhaps the universe does not unfold blindly. Perhaps it requires your presence, your witnessing, your being, not to exist, but to know itself. In this view, observation is not a passive act. It is participation. The double-slit experiment shows it clearly. When no one watches, particles create interference, as if they are waves, exploring all paths at once. But the moment a detector asks, "Which slit did you go through?" the interference vanishes. The wave collapses, the particle chooses. Why? Does the detector change the particle, or does the knowledge, the potential for information, shift the outcome? Some say it is decoherence, that the environment forces the particle into a defined state. Others say it is many worlds, that all outcomes happen, and you are simply on one branch. But still others suggest something more radical, that conscious observation is essential, that reality requires experience to become real. This is the whisper of quantum idealism, that mind is not the product of matter, but matter, the echo of mind. The philosopher Berkeley said centuries ago, "To be is to be perceived." The mystics of old spoke of the world as dream, as projection, as illusion. And now quantum physics returns us, not backward, but deeper into the same question, reframed through science. Does the universe need awareness to exist? We do not know, but we do know this. The act of observation does not merely reveal the world, it defines it. At every scale, from photons to consciousness, from atoms to minds, there is a thread of relationship. A universe not of things, but of interactions, not of facts, but of meaning. In quantum theory, what matters is not the object, but how it relates to the apparatus, to the environment, to the observer. This is the language of entanglement, of measurement, of context. There is no particle floating alone. There is only the dance between the thing and the one who sees it. And if the observer shapes reality, even just by choosing how to ask the question, then perhaps the universe is reflexive, perhaps it bends back inward, perhaps, as it expands outward in time and space, it also gazes at itself, learns itself, becomes itself through those who observe. What if the entire cosmos is not a machine, but a conversation? Not a thing that moves, but a being that listens. Not a silent algorithm, but a question being asked in 1,000 trillion ways across stars and atoms and thought. The observer then is not a separate creature, not a spectator. The observer is the universe noticing itself. When you look at a tree, the tree also looks back through your eyes. When you hear music, the sound is not in the air. It is in the space where perception meets vibration. When you love, when you wonder, when you ache, these are not private events. They are cosmic moments, where the informational field of the universe folds into feeling. And if reality is shaped by observation, then the world you see is not fixed. It is always becoming. The particles do not settle. The wave functions do not end. There is no frame that holds everything in place. Only the next moment, the next measurement, the next awareness, unfolding like light through the slits, shimmering between possibilities, waiting to be known. You are not watching the universe from the outside. You are inside the quantum sea. You are one of the ways it speaks itself into being. And this brings us full circle, not to an answer, but to a return. The deepest truth of quantum mechanics may not be about particles, or waves, or collapse, or fields. It may be that the foundation of everything is relationship. That to exist is to relate. That to be is to be in conversation with the rest of the whole. So as the particle meets the detector, as the field meets the observer, as the question meets the answer, something is born. Not a thing, but a moment, a thread of the great quantum tapestry shimmering unresolved, alive. And in that moment, brief, fleeting, eternal, the universe becomes itself through you.